Hello, Edu. We are seeing the presenter view, not the audience view. Edu, are you able to hear us? You can swap your display in the presenter view, I guess.
Professor, what? You mean what?
Yes. You need to swap your displays for your. There is a button on top left. You can click on that. Yes.
哦，你是这样子做，明白了。那你说那个丧尸，先 present review。
Yes, it works now.
Okay, good. Present review。 你看那个 desktop 图就没啥问题，直接弄 desktop 图没问题啊。
It's still a presenter view.
这个关了先，你先不管，用的好像是，你再试一下，我知道。把你的 desktop 1号给弄反了，我记得我刚才设置没啥问题啊。哦，那就不是别了，别了。
And there's the swap displays at the top. Top right.
Sucks. Oh my day.你好像是450可以了，你再写出。你问一下他们。Hi, Professor. Are we sharing now?
No, it says you started sharing, but we cannot see your screen.
And there's the swap displays at the top right.
是得学的。圆的，你再试试，先打开这个 ，OK。确实，这个他们是看到小的，正常还是4倍，好像可以再写上。
No, it's still presenter view.
Are we sharing now? Is this working now?
No,
It's presenter
sharing,
view.
but
看到是小的。
maybe you can mirror your screen. Don't use the double screen.
What now? Is that work?
No, it's presenter view.
Sure. 要干嘛？别 mirror，你 mirror 的话，我没办法 present view 了。Extend，对对，你不用，你现在就这样就挺好。他们看不到，看到的是这个。没有，他们这个是这个。你的，把它 streaming，I think so。streaming 肯定不是这个。streaming 的话，也。special present view。不就是把现在先slide 再点 zoom 啊，这很离谱吧？你先别 zoom 这个事儿，顶不了，现在顶不了，那另外一个屏幕哦，那先离谱。然后再然后再 present， 然后再是 screen。对对，行。Hi, the work?
It says you have started screen sharing, but the screen is black.
I think it's loading now.
Maybe you can wait for a while.
直接开始。
Are you able to mirror your screen? Hi, hello. Maybe you can just use this screen before you click on the slideshow. Yes, just use this screen. Is that fine?
Yeah, I think so.
Okay, yeah. Maybe you can start with this screen. You don't need to share your you don't need to start your presentation. Just use that screen. Yes, this screen. And click on slideshow. Maybe this can make the screen larger. No. Yeah. On the menu bar.
左右调一下。没问题，没问题，它就不按这个这个。Can you see the screen now?
It works. Yes, it works now.
Yeah, great.
Yes. Great. Do we need to record on the Zoom?
Yes. Yes, please. Oh, it's already doing a live stream, so you don't need to record.
Okay.
It will be starting.
Yeah, it works. Okay, great.
Yeah, great. Hi guys, sorry for the inconvenience. This is a little bit awkward. So good morning. On behalf of organizing committee, I warmly welcome you to the Robot Learning and SLAM workshop at ICCV 2023. Today, we gather to delve into the latest advancements in robot learning, perception, and SLAM. We're honored to have 14 esteemed invited speakers in our workshop, and this workshop will mainly have 3 sessions. The first one, hi, Professor, would you like to introduce this program?
Hello. Yeah, hello. Maybe I can take over. Yeah, thank you. So hello guys. Good morning. So welcome to the ICCV workshop on robot learning and SLAM. My name is Chen Wang. I'm now an assistant professor at University at Buffalo. So I was one of the organizer of this workshop, but due to my visa issues, I can't go to Paris. I'm so sorry about this. But I would like to introduce Shibo and Yidu to be the moderator. Here, Shibo and Yidu, could you put your hands up and let the audience know you? So, Yidu is my PhD student, and Shibo is a PhD student with Professor Sebastian Scherer. Okay, and next I just want to give a very brief introduction for the timeline. So there will be 3 sessions. 2 sessions will be in morning, and the 3rd session will be in the afternoon. So, in our original announcement, Zia should be the first speaker, but she has some personal issues and cannot make it in the morning. So we have exchanged her talk with the SLAM challenge, and so the SLAM challenge will be held by Wenshan and Shibo. So next, I will hand over the time to Wenshan and Shibo. Okay, you can take over.
So for the beginning, we will welcome Shibo Zhao and Wenshan Wang to present the pushing SLAM towards all-weather environments. Shibo Zhao is a PhD student at CMU Lab. His research interests cover 3D reconstruction and perception. And Wenshan Wang is a project scientist at CMU Lab. Her research interest is reinforcement learning and deep neural networks. So welcome, Shibo Zhao. Okay. Hello, everyone. My name is Shabo, and it's my great pleasure to have a talk and share some cool stuff with you. I'm very excited to have this presentation, and I'm happy to be able to be mentored by Professor Wenshan, Ji Zhang, and Chen Wang, and Professor Michael Keyes and Sebastian Scher. So without them help, this talk will not happen today. So for today's talk, I would like to share some 3 efforts that I'm working on to push the robustness of SLAM system. So the first, I will introduce our SLAM challenge. So it's from data set distribution, and it's a kind of the simulation to real world data set in SLAM challenge. And secondly, I will briefly introduce our amniocentric sensor fusion strategy to achieve robust SLAM system and able to online select the most informative sensor in the sensor fusion pipeline. And lastly, I will introduce the uncertainty estimation. So it's a hierarchical uncertainty aware multispectral odometry. So maybe we start with the application and motivation for us. In the past 3 years, I participated in several projects in CMU, including the DARPA subterranean challenge and off-road driving and welfare inspection to deploy our SLAM system in different hardware platform and environments. Our goal is very simple and practical. So just to build a SLAM system, not only for high accuracy mapping, but also for the robot navigation on the embedded system. So through this process, I found that the SLAM system is usually easy to fail in real world environments. So that will make me think about what's the potential problem for our SLAM system. So probably we need a more challenging data set. So why we need a challenging data set? So we found that existing data sets are relatively easy to run, which usually have a big gap from the data set to real world environments. So most of data sets are not challenging enough, and it only pursues the odometry and the mapping accuracy instead of the robustness and adaptation. So that came to our first ideas to improve the robustness of the SLAM system. So we need a very large data set which should towards all weather environments from the simulation to real world scenario, including the multi-node, multi-robot, and the multi-degeneracy scenario. So because of this, we release the Titan Air and Sub-T Mars data set from the simulation to real world. So the next, Professor Wenshan will introduce the Titan Air data set to us.
Thank you, Shabo. Can you hear me?
Yeah, we can hear you.
Cool. So some of the trajectories in this challenge are coming from Titan Air dataset. So we published this dataset in 2020 and targeting at pushing visual SLAM to solve long-tail challenging cases. Another main objective is to facilitate learning-based odometry and SLAM models by providing large-scale training data. We collected data in 20 diverse environments in all kinds of challenging cases. The data was collected in photorealistic simulations so that we can get reliable ground truth and multimodal sensing data. The Titan Air dataset is well received in the community, and we see an average of over 1 terabyte download every day. It was used in CVPR 2020 SLAM challenge. And this year we expand the track to LiDAR SLAM, which is a result of a new version of the dataset, which I'll talk about later. So we see a trend that Titan Air is used more and more for learning-based SLAM because of its diversity in scenes and motion patterns. That's an advantage of using simulation because previous SLAM datasets collected using physical robots are constrained and biased by the hardware. Only in simulation, you can generate these random motion in 3D space, which allows you train a model that can be generalized to all kinds of robots. In this SLAM challenge, we provide both simulation data and real-world data. One thing we want to see is how well a learning-based method can be generalized from simulation to real world. So we are very excited to announce that PartnerAir V2 is coming with a more ambitious goal of pushing the research in general robot perception instead of just the visual SLAM. In general, V2 contains more environments, more modalities. It's more challenging, less biased, and more flexible. V2 is one order of magnitude larger than the previous version. The data from this challenge is from V2, which provides more modalities. We started to see more and more algorithms, not only for SLAM, but also for depth estimation, visual transformer, and multi-model pre-training, and even foundation model that take advantage of a data set. We increase the challenging level even further in the second version by adding lighting conditions, changing the seasons, adding dynamic objects, simulate the day-night circles, adding all kinds of weather conditions, and providing tools to add realistic features like motion blurs. Our data set is not only a set of pre-collected trajectories, we provide tools that allows the users to customize the data according to their own needs. On the left-hand side, you can see the raw image provided by our data set. Users can arbitrarily change the camera intrinsics, distortion, and camera orientation to get the types of training data they need. As shown on the right side, for example, people from self-driving community could remove the roll and pitch rotation of the camera by resampling the images. Our target is to facilitate development of generalizable models that can work on different platforms with different types of cameras or LiDARs in challenging scenes. Okay, yeah, back to you, Shpo.
Okay, thanks, Winshan. So that will help us to announce our ICCV'23 SLAM challenge, because it's combined the simulation data set from the PartnerAir and the real world data set from Sub-T Mars, including the off-road, carrying, indoor, cave, dust, and smoke illumination changes environments. So the ICCV'23 SLAM challenge provides its more diverse data set compared to the existing KT data set or Europe data sets. So here is the introduction for our ICCV SLAM challenge. So we are pushing the SLAM towards always environments because we believe that robots need to work in some challenging environments to save people's life. Okay. So in our up to now, so they are in our ICCV Slam challenge. So here I would like to have a brief summary. So up to now, there are roughly 1,800 visits in 2 weeks, with 120 unique visitors in our websites. And up to September 25th, there are already 15 teams among finished the challenge report. The final subchallenge report is roughly October 15th, and the final ranking will be released around the October 22nd. So we will schedule another meeting to discuss all the solution. So for the latest news, please check the our website. Okay, so however, is it enough just providing the large data set to improve the robustness of SLAM system? So the answer is no. So we believe that a sensor fusion algorithm should always be improved. We believe that a robust SLAM system should have online adaptation capability for diverse environments. So to solve this issue, and we believe that probably the amniocentric sensor fusion might be a better way to overcome degeneracies. So instead of combining all sensor data into a full-blown factor graph, superodometry divides the big factor graph into several sub-factor graphs. So it's called the visual odometry factor graph, laser odometry factor graph, and amniodometry factor graph. So our system follow a very key insight. So we believe that amnio and its system estimation can be very accurate as long as the best drift is well constrained by other sensors. Therefore, superodometry uses the amnio as a primary sensor. It uses observation, provides the visual initial odometry, LiDAR initial odometry, and constrains the acceleration bias and the general acceleration bias. So in return, the constrained amniodometry provides the prediction to the YO and LIO, which recover the motion in a coarse-to-fine manner. So to adapt to different environments and applies online adaptation and to select which sensor to constrain the bias of amnio when the environment is changing. So because of the time constraints, I cannot explain too much about this algorithm. So for detail, please check our paper. So here is a summary result from superodometry, and we test the superodometry in various challenging environments. And this is happening in the DARPA subchallenge challenge. And in the beginning, the small drone actually is out of control, but even this happens, and superodometry can still overcome the rotation of the small drone. And we also test the superodometry in the dense smoke environments. And it's working well because it's using the thermal camera to overcome its estimation. So we also test superodometry in the multi-robot mapping, and in this test, and all the robots running superodometry together, and to share the map between each other. So we test the superodometry on the small drone and the ground vehicle in this environment, and this is a map from the other robots, and the different color represent the map from different robots. So you can see it lines very well. And we test the superodometry in the large scale mapping, and it's roughly 10 kilometer trajectory, and the mapping quality looks good. So we also test the superodometry in this off-road test, and it's a high speed and it's open area, and it's very challenging to test SLAM algorithm in such area, but because we fuse a visual GPS together, and it can still solve this problem. And we test it in the kernel environments. And this kernel is roughly 1 kilometer trajectory. And in this scenario, we use the visual odometry and to help the superodometry to overcome the drift along the forward direction. And this is the mapping result we obtained from the algorithm, and it looks good. So we also test it in the Lego robots and with the multiple floor mapping, and from indoor to outdoor, and
In this scenario, I think the big challenge is that because the LiDAR usually cannot provide enough constraint in the Z direction. So because we use a visual sensor to assist this LiDAR solution, so it can still work well in such environments. So we also test the algorithm in the snow environments. So here is the left figure, the right figure shows the summary result from superodometry. It can overcome the multi-degradation, include both geometric and visual degraded environments, and support multi-robot mapping from different robots. However, is that possible to apply the adaptive fusion ideas on visual-only SLAM system? The answer is yes. So we will introduce our third work. It's called multispectral odometry. So the third idea I want to share with you is that we believe that a robust visual SLAM system requires the multispectral fusion and the uncertain aware capability to predict the potential failures from low level to high level. So why we need a multispectral odometry? So from the figure, you can see that our visual spectral can only provide a small amount of information from the whole range of the spectrum. There are a bunch of the information actually we didn't make use of. Therefore, we believe that multispectral imaging is a promising solution in challenging environments since it can capture invaluable data in multiple spectral bands, including those beyond the human eye. So here is a proof of the feature extraction from the RGB spectral and the thermal spectral. We found that their feature tracking results are complementary. So therefore, you can see that the feature in the RGB spectral, actually there is a lack of features on the car, but in the thermal images and there is a feature on the car. So it's kind of, therefore, it seems like it tells us that the multispectral odometry is a good option for the challenging environments. So how to achieve the uncertain visual odometry? MSO is made of the three, so I would like to introduce our pipeline. It's made of the three major components. It's called adaptive fusion in 2D, adaptive fusion in 3D, and adaptive fusion across engine. So first, adaptive fusion in 2D employs the lightweight thermal point network. We first use a thermal point network to achieve robust feature detection on both thermal and RGB images. Then we track a sparse set of features to perform the images in the scale space pyramid in a top-down manner, where the cross level provide initial transfer gas for the next level by minimize the photometric error. Instead of treating each feature equally and assuming the intensity residue are normally distributed with unit variance, we analyze its intensity residue distribution and propose uncertain aware strategies to identify the most valuable features towards the robust pose estimation. Given that we have already estimated uncertainty stemming from the 2D photometric error, so it naturally raises the question that how to extend this 2D uncertainty into the domain of the 3D space, bridging the gap between the 2D images and the 3D geometry. The figure shows the uncertainty estimation from the feature extraction. So we can see that the feature located in the corner has smaller ellipse and a high confidence, while the feature located on the line have a lower confidence along the line direction. We use the uncertainty transform to sample the location of the pixel from 2D uncertainty. For each sample, we can obtain the Bayer vector from the 2D and into the 3D space. The right figure shows the sample processed from 2D and to 3D space. And finally, the intersection of two Bayesian vectors between the host frame and the target frame represent the sample of the uncertainty in the 3D space. However, that is just discussed in the two-wheel uncertainty estimation. One crucial insight for estimating the 3D uncertainty is that the uncertainty associated with the landmark will diminishes as they are observed from the multiple viewpoints. So at the beginning, so it's roughly have two wheels and the uncertainty roughly have a big ellipse, 3D ellipse. However, as the landmark is visible by multiple times, and the estimated depth will convert to the ground truth depth value as the number of wheels increase. So for each set of the co-visible 3D points observed from the multiple frames, their depths can be conceptualized as the 1D dimensional Gaussian distribution problem. By evaluating the coherence for 3D landmark, we can distinguish between the inlier and outliers and reduce the depth error for the 3D points. And finally, I would like to introduce adaptive fusion across the engine. So active selects the most informative measurements between the uncertainty estimation from the 2D to 3D, even achieve the seamless software switching scheme across modality based on the change of the environments. So basically, it includes two components. The first is a merit weighting. Instead of describing the entire frames or sensor data, so our pipeline evaluates the quality of each measurement and sets them with different weights. And we also actively select the constraints. If there is a substantial depth variance from 3D points or pixel variance from 2D pictures, and their corresponding mark will be removed. So we achieve the adaptive fusion from the 2D space, 3D space, and finally achieve adaptive fusion across the engine. So it's the adaptive fusion from the low level to high level. So in this experiment, I want to show the performance of our MSO pipeline. The right video shows the real-world experiment, and the left video shows the experimental result, including in the feature extraction on multispectral images and odometry results. So at the beginning, so our drone is flying into the smoke. So we test our pipeline in the dense smoke. In this event, RGB usually provides rich information compared to the thermal camera. We also test our pipeline with several bumps and to see if our pipeline can overcome some aggressive motion. So the right figure here shows the feature extraction on the thermal images and the RGB images. And the bottom shows the odometry result from our MSO pipeline. And we test the MSO in the low lighting condition, and in this environment, the RGB is roughly similar to the thermal camera and to contribute to the odometry. And it also includes a complete darkness in this environment. So in this case, and we will believe more on the thermal odometry compared to the RGB odometry. And we also test the MSO in very dense smoke environment. And in that case, it will completely degrade to the thermal odometry pipeline. So by assessing the uncertainty for individual 2D features and 3D landmark, so MSO can set different weights for each constraint in the optimization and select the most informative measurement and to achieve soft switching across in the modality. So basically here is the summary of our MSO pipeline. The first, we propose a multispectral initial state estimator. And secondly, we propose a hierarchical adaptive fusion pipeline and export uncertainty from the 2D features, 3D landmark, and engines. And thirdly, it's a multi-camera system and support an arbitrary number of thermal or RGB camera setup with various camera model. And lastly, it incorporates the learning features with the radio with the traditional method and to achieve real-time performance. So this is the first time and we are making the visual odometry pipeline to possible to overcome both darkness and smoke environments. The endpoint error actually is roughly 4.08 meters within 173 trajectory in this scenario. As our drone navigates through the both smoke and the clear darkness environments repetitively, so our pipeline adaptively transition between the modality from the visual odometry encoded in the green trajectory, multispectral odometry encoded in the blue trajectory, and the thermal odometry encoded in the red trajectory. Okay, I think it's time to close our discussion here. So for today's talk, I just want to share the 3 messages to improve the robustness of SLAM system. The first, in the data distribution level, we believe that our SLAM requires data set towards all weather environments from the simulation to real world. The second thing I want to share with you is that in the sensor fusion perspective, our SLAM requires adaptive and adjustable capability for diverse environments. Probably, amniocentric sensor fusion pipeline might be the better way to overcome all these degeneracies. Lastly, in the correspondence perspective, our SLAM requires the uncertainty-aware capability and should be able to predict the potential failures from low level to high level. So robots, actually, we believe that it's not limited to the household robots. Actually, it is for the better human understanding. We believe that robots should also include the field robots and could be operated in some challenging environments to save the people's lives. Thank you.
Thank you, Shibo Wenshan, for that insightful presentation. And now, let me introduce our next esteemed speaker. Sure.
Okay. Okay. Share screen. Okay. Oh, is it working fine? I think we forgot to share screen. In the Zoom and share screen. Yeah. Okay. I think in a second. Yeah. Okay. It's working. Yeah, it's working. All right. It's okay. Yeah. Okay. Cool. So you can present to me. No, we'll see. Okay, cool. Okay. Okay, thank you very much. My name is Maurice Fallon. I'm an associate professor at the University of Oxford. I'm going to talk today about our research in multi-sensor SLAM and robot navigation. Our team focuses on multi-sensor systems, and we try to drive things towards mobile autonomy in the same way as the CMU team have talked about. Focus quite a lot on legged systems because they kind of embody all the mobile sensors that we have on self-driving cars or aerial platforms. For example, high quality IMUs, again, in the same manner as Shibo mentioned, are quite central to robot navigation. And legged systems have joint sensing, joint kinematics. I won't talk too much about those today. Obviously for environment sensing, depth cameras, and then moving up to things that are more about navigation, external facing cameras and LiDAR systems. So the same kind of multi-sensor fusion that was talked about in the previous talk, and also the same kind of test environment. So this is the DARPA challenge. And we see the animal robot with locomotion controllers from our colleagues at ETH, exploring the environment where it's entirely pitch black and the robot's carrying on board both lighting and its own sensors to map and navigate the environment. And you can see these kind of degenerate scenarios that occur where the robot needs to be able to fuse together sensor modalities, not just operating off of a single sensor, off a single sensor, whether it's legged kinematics, which is typically very robust but low, but having some degree of drift, laser, which in very narrow environments like this struggles to form 6 degrees of freedom constraints, and vision, which can struggle in different lighting conditions. So our research in Oxford has developed a multi-sensor suite called VLANs, which combines together these different odometries. So reaching back a few years, this is an illustration of multi-sensor visual odometry plus kinematics. So the contribution from the legs effectively is a kind of noisy measurement of velocity on the assumption the robot's foot is in contact with the ground, and that velocity measurement can give you slowly drifting odometry. But incorporating that with vision is illustrated in the video. Here, a rather typical approach of sparse visual inertial odometry, and done in the right way to be able to, for example, back out inherent biases in the legged contribution can give us a good incremental motion estimate. As we move to the DARPA challenge, for example, the question arose of how to incorporate LiDAR, as it's ultimately the most accurate sensor in these kind of environments. And here are a few examples from the literature of different approaches that used, for example, different kind of multiplexers or health evaluation modules. So multiplexer is effectively a switch between different sensor modalities. If you determine one modality is failing, like your LiDAR, fall back to your vision or fall back to your wheel or leg odometry. And health monitors are effectively those components. Typically, these are loosely coupled approaches. And we wanted to look to develop something that was a bit more tightly coupled with vision and LiDAR. So we're retaining the sparse visual feature approach, but then we also wanted to develop a feature-based approach for the LiDAR fusion. So from a LiDAR point cloud, we wanted to be able to extract features from the environment, so edges or planar patches, to track those over time and to merge them in the same estimation framework as we were carrying out with vision. So least squares, windowed optimization, and these are the different factors. So an IMU prior for pre-integrating the IMU related to work from Luca, for example, planes from the LiDARs, edges or lines observed from the LiDAR, and also visual features tracked from the camera system. Again, a windowed optimization that fuses those together. And we deployed that in a variety of tests in the run-up to the DARPA Subterranean Challenge. And you can see here an illustration of operating in a mine environment. This is a top-down view, and there's a green line which corresponds to ground truth inferred from a prior scan with a tripod-based system. And you can see that there's very little drift in this environment. Moving towards sort of more challenging environments here, entering a narrow corridor, a narrow tunnel in a disused mine. In this scenario, you've no LiDAR constraints in the up-down direction, and in the longitudinal axis, it's ill-defined. So we're switching between the modality, or not switching between the modalities, but fusing different components of the modalities together. So that approach was quite successful, but one of the challenges, quite successful, very accurate, quite robust to different sensor redundancies, but ultimately the LiDAR system tends to be the most accurate. And a kind of a reflection from that is that a different approach that maybe that recognizes that there's sort of fundamental variations in the relative accuracy of the sensor modality is important. And I did like the presentation earlier, which touched upon how we can do this. I feel a sort of a LiDAR hierarchy based off of the perceived or the expected accuracy of the different modalities is important, and super odometry is one contribution for that. Moving on from odometry per se to large-scale mapping, wrapped around our odometry system, we have a large-scale SLAM system. This is just an illustration of the work. It's not necessarily a particularly novel contribution, but it's a large-scale multi-factor, multi-sensor laser-based mapping system that can scale to large-scale facilities and in a very accurate manner. Since won a couple of mapping competitions in 2021, and it can also be adapted from the robotic system to more handheld applications. In 2021 and 2022, we were participants and then organizers of the Hilti Slam Challenge, which has been quite impactful in robotics, collecting very high accuracy ground truth for the sensor system. Specifically trying to target millimeter accuracy by using very high accuracy tripod-based systems that you can see in the bottom left to capture very accurate prior models, and then placing a handheld sensor payload at crosshairs throughout the facility to be able to back out at reference points millimeter accuracy of the sensor payload. So as maybe the arc to observe is that as SLAM has become more accurate, moving down from meters of error to centimeters, then the necessity to have multi challenge data sets like the one that was just been presented for the by the organizers, but also for going down to extreme accuracy as well. So if you're interested, I suggest checking out the Hilti challenges. On the back of that and using those data sets, then we've been able to develop multi-mission fusion. So this is a bundle adjustment based approach to merging together different missions into a single combined reconstruction, with the red edges indicating loop closures between different missions on different days. And this starts to open up different applications for long-term monitoring. But obviously, to be able to join those missions together, you need to be able to create constraints between missions, and that's effectively the problem of LiDAR-based place recognition or localization. So this is a work that we call InstaLock, which takes an instance-based approach to indoor LiDAR localization. Obviously, there's a vast amount of work done on outdoor localization using things like Kitty. Here, we wanted to focus on LiDAR-based indoor localization. LiDAR-based because if we're operating in very poorly lit situations, then vision would be a modality that we would struggle with, although we would use that as well. And we're using a kind of wide field of view LiDAR. So you can see that this particular LiDAR has a larger field of view. So it's getting something akin to a full point cloud reconstruction of the environment. The first step of the approach is to carry out panoptic segmentation, to segment out different instances of objects that are present. So walls, tables, benches, chairs, ceilings and floors, and then relative to a prior model, identifying those instances, creating matches between them, and then using that to back out pose estimate within a prior model. Just a little bit about the method. We're using the software method to carry out a panoptic segmentation. And then we're identifying a single descriptor by pulling down the individual object instance point clouds. So by definition, this requires a relatively dense LiDAR. It's not necessarily going to work with a 16 beam LiDAR scanned in an indoor environment. Here we're using 64 or 128 beam LiDARs. We train the method entirely with simulated data. So this is data synthesized from the Unreal Engine using the AirSim plugin. And that obviously avoids the need to do hand labeling. So we're extracting the semantic label directly from from the simulator. And this is an illustration of some of the environments. So this is one of the buildings in Oxford. So multi-floor reconstruction is the prior model, and individual instances of point clouds are what we're matching against. So just pause the video here. You can see a single LiDAR scan at a particular instance in time is being segmented into different object instances. And then those object instances, when there's a successful match, is shown here. So you can see different instances, and they're being matched to the prior model. Where we have sufficient number of those, maybe in the order of 5 object instances that are successfully matched, we're able to use a Ransack-based approach to infer the pose estimate. So as you see the video going along here, you can see flashes of near parallel lines. Those correspond to successful loop closures. And you can get a feel for the precision and recall there. So it's sufficiently accurate to be able, or sufficiently high recall to be able to be used as a place recognition algorithm without needing to rely on vision, which would be a typical approach in this kind of scenario. On the basis of this kind of work, we've formed a spin out recently to move towards monitoring construction sites, doing repeated scanning, and here are some illustrations of the kind of capabilities you can determine. So this is relative to a building model, being able to identify construction errors or deviations relative to plans. Okay, so up to this point, I've only talked about LiDAR based, and there's not really been any vision except for its contribution to odometry. Obviously, there's been an explosion of work in the nerve space, and it kind of attaches or is adjoint to the problem of SLAM. However, these kind of approaches typically tend to be object-centric, so scanning around objects with views pointing towards objects, while the robotics context, particularly robots that are in inspection environments, typically move to the scene and aren't going to orientate their sensors so as to be to kindly reconstruct an object of interest. But we do have the capacity to augment our sensor system. So this is a sensor payload we've been developing for a few years. It's made up of wide fisheye cameras that are pointing in 3 different directions, forward, left, and right, as well as a wide field of view LiDAR. So we're instead of creating an object-centric and based nerve reconstruction pipeline, this is a trajectory-centric approach where we instead have sensors pointing in different directions. Before getting into that, of course, the key challenge is the multi-sensor aspect. So calibration between the sensors is crucial. Here you can see using the CAD model to directly project the CAD prior to project the LiDAR into the camera image. So you can see it's coarsely overlaid. You can see the LiDAR intensity in purple kind of overlaying on the black. That's low intensity, and high intensity LiDAR returns are the green and yellow. We're going to use that cue to precisely align the scans. A typical approach would be to determine the boundary of a calibration target, as you can see here. But that's quite difficult to use in practice. It requires the human to know about the field of view of the LiDAR. Typically, the cameras have got sufficiently large field of view, but the LiDAR can be very small field of view. So you can get a feel on the left-hand side about how far the operator of the calibration system would need to be able to fully capture the calibration target. So instead, we're able to operate on partial views of the calibration by creating a differentiable calibration module. So we've detected the calibration target in the upper parts of these images, and then we construct this calibration pattern, and that can create a differentiable alignment target. So we're able to co-register the LiDAR to this calibration target, as illustrated here, and without the necessity for there to be full overlap. And that also allows us to be able to create more diverse views and to achieve kind of 1 pixel error in our reprojection of the LiDAR. So armed with 3 LiDAR images, LiDAR depth images, and 3 cameras that are directly overlaid with one another, our trajectory from our SLAM system, that our nerve pipeline first refines those poses using CalMap. So we do find that a final refinement with CalMap does improve the PSNR of our nerve reconstructions. But in many cases, the trajectory that we provide with our SLAM system is essential, because CalMap otherwise can't actually estimate the trajectory without a prior. So that gives us both a speed up and a robustness improvement. And then as we look to the NERF reconstruction, if it's just a vision-based approach in these texture-free environments, as you can see with NERFactor, which is a baseline approach, or the approach we adapted from, this gravelly area on the texture-free environment is unable to reconstruct the scene. Using the depth is a good step in the right direction. We can see that it's starting to provide a reconstruction as observed from the surface normals, but then moving on and computing normals directly on the lighter point clouds, and the point cloud reconstruction gives us an extra boost here. So we're starting to see both in the texture-rich environments, but also in the texture-poor environments, that kind of reconstruction. So here's the sort of the A of visual-only pipeline from NERFactor. And you can see, in particular in this portion here, where there's very little reconstruction, while in the LiDAR aided approach, it's both got a geometric backend, so there's a point cloud that can be extracted from this reconstruction, but also we're able to reconstruct the views that only have a sort of a single passing sweep by this drone platform that collected this data. Here's another large-scale reconstruction. It's broken up into several submaps. Still working on the submap approach, but you can see the incorporation of the LiDAR, which contributes to the overall reconstruction. Yeah, some takeaways from this are that most of the data was taken from autonomous robots operating on with a traditional SLAM approach. The SLAM trajectory greatly speeds up training time, and it is necessary still to refine the poses and the intrinsics with the COMAT-based bundle adjustment. And just to re-emphasize the point, there's a point cloud geometric backend to this. It's not simply a rendering-based pipeline. So this is the point cloud that's taken from the overall system. Okay, so moving on to kind of a purely vision-based topic. We looked at the emergence of LLMs, and we wanted to look at how they could contribute to semantic-based mapping to sort of break down the approach typically used in SLAM, which has developed traditional feature-based place recognition modules that are kind of hand-curated, things like Debo, for example. Building upon our multi-sensor odometry system that I mentioned previously, specifically multi-camera odometry, we have a camera system that has overlapping field of view, slightly overlapping field of views, and that allows us to be able to implement multi-camera odometry, where visual features are tracked in a forward-looking camera, but then they can be moved to cameras that are on the left and right of the facing. So here you can see the sensor approaching a wall, and where there are visual features are deprived here, we can start to track features that have been passed to the left and right cameras. So armed with this as a source of odometry that can work in very narrow and confined environments, such as this narrow staircase here in Oxford. So this is a ground truth trajectory in green, and as Linton is carrying the device up the staircase, you can see how tight it is, and the need to be able to have different camera systems that are able to contribute to the odometry, not just a small field of view RGB camera. As it comes back down, you can see that there's very little drift. So effectively, within narrow confined spaces, we can compute an odometry source, taking advantage of the clip model. We're able to take image snippets and to be able to extract a semantic encoding with an open vocabulary. And then we're starting to build up a semantic map on top of our visual pose graph. So this is the kind of scenarios where we want to operate on, where robots are moving around or sensor systems are moving around in natural environments, not really making the goal of building a visual map, but it's coming about through their natural motion. Here you can see an illustration of a pose graph being built, and as images are coming into the system, semantic labels being extracted for a particular node in the pose graph using the clip model. So in this case, we have an office label for a particular point, but then across all of the nodes, we have the different classes, so corridor, office, kitchen, and so on. And here you can see how we've refined the mapping system by first segmenting into different classes of rooms, then using some geometry. So changes in the elevation are useful to be able to distinguish between corridors and staircases, while then we're able to also use the transition between corridors and individual rooms to extract individual rooms instances. So just show a little video clip of that system. I think I'm coming close to the end of my slot. You can see this is a 3D view of multiple floors. So you can see the first floor of the building here, corridor spaces in different rooms, staircases being extracted in part because of the change in height, and then coming down to the ground floor. And another example of that on a simulated data set from Lucas Group. We're interested in using this in assistive technology. So this is a prototype we've built for a human wearable system with a focus towards assistive technology. So it combines the multi-camera system plus some depth cameras for environment reconstruction. This is just an illustration of the challenges of putting this kind of multi-sensor vision system onto a walking system. So this is the footage of the camera being undulated because it's attached to the thigh of the person, and you can see the trajectory of the visual odometry system. It's a bit disimproved compared to what I'd like it to be, but we're kind of just setting out to build this application. Okay, I think at that point I'll just skip over my last topic and take any questions. Okay, thank you very much. Questions? Luca?
So for the last working with features to classify the semantics to different rules, and we are considering mostly like a lot of different rules. How does that scale of the large number of classes we have some
I think we want to move in that direction. I think it is difficult to get access to lots of private places, and MIT has an open campus, which makes this kind of data collection. We've probably gone as far as we've been able to go with the access to the sites. So we'll see as we move forward. It's a good question though. Okay. Well, thank you very much for there's a question. We specifically built it for indoor environments because we could train it with simulated data, and we also kind of built it to a degree because we know that outdoor environments is a very heavily explored environment. In structure, it's not dissimilar to approaches like I forget the name of the system from René Dubé in ETH, SegMatch, extracting individual segments, having a database of segments and matching them. So the structure of it is quite similar to existing outdoor approaches, and it would determine on the learning and training. But it would likely work as well outdoors or appropriately outdoors. Okay, Matt.
Okay, good work. I have just a question to follow up on that. So the physical persistent rating of 91%. What do you do about those small positives?
We maintain a trajectory estimate from whatever other sensors are on board, and then carry out yeah, effectively. I guess the real challenge is that with LiDAR point clouds indoors, they're really quite indistinct. So being able to achieve recall, particularly if you move to kind of construction environments that are very bare and barren, that's really quite the focus rather than the precision. Yeah. Okay.
Thank you for the nice work. I'm very interested in your research on the overkill data set, which is we are working a lot of us. I noticed that you make use the real features located on the glass. Have you used the other measurements? From my point of view, the real point on the whole and purely makes the generation piece, but the trend ratio is located and quite well.
I think
provide more detail about that.
I think you're talking about this work way back at the start on mapping in sort of natural environments here. So going out into this sort of open environment here, it's a sort of natural environment, tracking visual features in that scene. Is that what you mean? I guess LiDAR-based approaches in sort of natural environments are on a feature level is something that we struggled with, and that was one of the things I pointed out to as why we've reconsidered having feature-based LiDAR approaches in natural environments. In those kind of environments we needed to rely on necessary or to a great degree on constraints from vision. But generally the visual odometry works quite well even in those kind of environments, particularly with a downward facing camera. It's scanning on the ground. Okay.
Thanks a lot for great stuff. We appreciate the historical knowledge by Dr. Boris and welcome Dr. Luca.
Right, folks, it's great to be here. Today I want to present work from my group on the work we're doing on robot perception, and I would like to touch on three main aspects: hierarchical representations, certifiable algorithms, and self-supervised learning. Typically, I cover these topics in a much longer presentation, 1 hour presentation. So in this case, I will keep it short, and I will keep it a little bit high level. With my group, over the last few years, we've been pushing, we've been pushing the state of the art in robot perception and SLAM in three main directions that I'm summarizing in this plot. Some of these directions are pretty intuitive. For example, robustness. We like algorithms which are more robust to noise, outliers, and domain shift. We would like algorithms which are more scalable in terms of the scene size and supervision. But at the same time, if you look at the vertical axis, we are also trying to push for algorithms which enable a higher level of autonomy and scene understanding. So just to make sure we are on the same page about this, you can think about the state. Example of scene understanding. If you are very low in terms of scene understanding, maybe you just understand the geometry, and you can tell the robot to go to position X, Y, and Z. We are pushing for robots that have a little bit of a higher level understanding and can execute complex instructions, such as go grab me the cup of coffee on the desk. So just to make sure you're on the same page about these three axes, let's populate maybe in a qualitative manner a bunch of data points in this plot. You can think about the state of the art in SLAM being roughly the one I'm showing in the plot. We have developed a lot of robustness. Algorithms are pretty much plug and play. They're fairly robust, and they scale to fairly large environments. For example, the map I'm showing here is some multi-robot SLAM dataset covering tens of kilometers of trajectories. At the same time, SLAM algorithms, the traditional instantiation of SLAM algorithms is mostly about geometric understanding. So we'll not have a lot of components on the vertical direction. They will not have much scene understanding. On the other hand, if you look at the state of the art in supervised deep learning and 2D semantic segmentation, here you start getting semantic information. So you get a much higher level of scene understanding, but these techniques are mostly bound to operate close to the trained domain. Therefore, both the robustness and the scalability is pretty limited. And of course, things go even worse if you're thinking about 3D deep learning instead of 2D. So what we want to push for, the goal of our research is really to develop scalable, robust, self-supervised algorithms for real-time scene understanding. In the rest of this presentation, I have three parts. I'm going to tell you about the progress we have made, again, at a high level along the three directions of this plot. And I'm going to start with the direction of scene understanding. So part one is about high level and large scale scene understanding. And I'm going to tell you about the transition we are seeing, which is going from SLAM to metric semantic mapping and 3D scene graphs. So why do we need metric semantic mapping? Well, of course, if I want to tell my robot, go grab me the cup of coffee on the desk, the robot will need to understand the geometry of the environment in order to avoid obstacles, but we'll also need to understand the semantics. We'll need to understand where is the cup of coffee, where is the desk, therefore we need metric semantic maps. Starting in 2018, we started pushing on a real-time metric semantic SLAM techniques, and at this point, many of you have seen Chimera. Chimera is a library for metric semantic SLAM. Is taking standard camera and IMU data, is using 2D semantic segmentation, and then is back projecting the semantic segmentation into a 3D metric semantic mesh, which is the one that you see here in the video. But we are not the first, of course, to think about metric semantic SLAM. There is Andy here in the audience. This is largely inspired by semantic fusion, a mesh-based version of semantic fusion. And of course, there are many new proposals, like about metric semantic SLAM. The things that still stand out to me about Chimera is that there are three elements. First of all, we are doing this post-graph and mesh optimization, in which we're able to deform the entire mesh in response to loop closures in a very efficient way through a post-graph optimization problem. And also, we have a lot of robustness in correct loop closures through a tool which is called graduated non-convexity. And everything is running on CPU, which is pretty interesting considering that most of the other approaches are GPU-based. So going beyond Chimera, we quickly realized that metric semantic maps, this kind of meshes or flat metric semantic maps, are not enough for the type of scene understanding and for the type of autonomy we want for our robots. For instance, again, if I want to tell my robot, go search for survivors near the fridge in the kitchen, a metric semantic map will not be very useful. The metric semantic map will not tell me where is the kitchen. It will not help the robot reasoning over relations between objects. For example, the fact that the survivors might be near the kitchen. In other words, in order to execute complex instructions, robots will need two extra things. The first one is that we'll need to understand semantics beyond objects. They will need to understand rooms, buildings, agents, and so on. Moreover, we need a representation which is able to reason over relations between elements in the scene. For example, the fact that the fridge is within the kitchen. So over the last few years, we have been pushing on novel map representations, and in particular, 3D scene graphs, which are metric semantic in nature. They also consider semantics beyond objects, for example, rooms, buildings, and so on, and they also capture relations between elements. So a 3D scene graph is the representation that you see here in the video. Essentially, at the bottom layer, you have a dense metric semantic mesh. But as you go up in the hierarchy, you're abstracting away the dense geometry into abstract semantic concepts, being objects, agents, rooms, buildings, and so on. Here, the layer of places and structures. Structures are essentially walls, ceiling, and so on. Places are a topological map representing traversability of the free space. So our contribution has been to push on this representation, really develop real-time algorithms that are able to build this representation from sensor data as the robot moves through the environment. So this effort led to Hydra, which is the name for our pipeline, for our system for real-time 3D scene graph construction. Hydra will start, essentially the robot will start without prior knowledge of the environment, and through Hydra will slowly reconstruct the 3D scene graph of the environment itself. For example, while moving, we'll populate a metric semantic mesh of the environment. At the same time, we'll estimate its own trajectory, which you see in purple here. We'll extract objects from the mesh. We'll also identify skeleton of traversability, like this graph of places out of the free space of the map. And we cluster the graph of places into rooms, buildings, and so on. So this is the first kind of nice extension to SLAM. Now we are not only doing SLAM, we're also thinking about 2D semantics, which is projected back on the 3D mesh, but also to reason over rooms and buildings and so on, as well as places. We are starting to use other tools, such as graph theory, topology theory, and so on. So through Hydra, we're able to get essentially a geometric clustering of the rooms, buildings, and so on. Of course, this is all open source, but it would be also nice in many cases to identify which type of rooms the robot is moving in. For example, here we identify that there are 2 rooms, but we don't know if a room is a kitchen versus a bathroom. Therefore, we also pushed on new architectures for graph neural networks to classify nodes in the scene graph. And in particular, we developed the neural tree architecture, which is an architecture with provable performance guarantees that taking objects in a room will classify which type of room the robot is moving in. So the ultimate result is something like this. The robot is starting in a completely unknown environment. In this case, it's a kitchen. And as it explores, it's building the mesh representation of the environment, is estimating its own trajectory, is clustering different objects and identifying the semantics of this object. You can see the sink, appliances, chair, table, and so on. And then this neural tree architecture is going to populate the semantics of the different rooms, for example, kitchen, hallway, and so on. In the latest paper about Hydra, I also proved a fairly fundamental result, which I really like, which is this kind of 3D scene graph representation can be understood, of course, as graphs, where the nodes are spatial concepts and edges represent relations. But this kind of hierarchical representations have low tree width, which means the tree width is a measure of complexity of a graph. If you prove that the graph has low tree width, essentially you're proving that you can do efficient inference over the graph, which is a pretty cool fundamental result. So we're doing robotics. So the nice thing is that we designed Hydra to be lightweight enough and to balance the use of GPU and CPU in a way that can run in real time on a robot. So in this video, I'm showing Hydra running on a A1 quadrupeds. So you see the robot moving in the environment. You can see the 2D semantic segmentation, and then you see the scene graph being built in real time, as well as a top view of the scene graph, which is showing up over there. So the scene graph is making sense here. The scene graph is picking objects, is clustering different rooms in the environment. But probably the most important part of this slide is the runtime table that you see here. So the runtime is describing the time it takes to build a layer of objects, places, and rooms in Hydra using Xavier NX. Xavier NX is just a small credit card-sized computer. And you can see that we can build all the layers in a matter of milliseconds. Our work has been also pushing on extending these pipelines for metric semantic understanding and 3D scene graphs to multi-robot systems. Here I'm summarizing just two main efforts in a single slide. On the left, you see Chimera Multi, which is an effort to extend Chimera to multi-robot systems. This is been something we've worked on for a long while. We have transactional robotics last year, but also we're still working on deploying these on real problems. And indeed, we have a new paper at IROS 2023. The idea in Chimera Multi is to have multiple robots building metric semantic meshes using Chimera, but also the fact that when the robots are meeting each other, they can find loop closures and compute a globally consistent trajectory through distributed optimization. So the approach is fully distributed. We'll get a metric semantic mesh of the environment, and is also robust to outliers in the loop closure detection through a distributed version of rather than non-convexity. At IROS this year, we also went a step further, thinking about multi-robot extensions of 3D scene graph construction. And we have Hydra Multi, which is the multi-robot extension of Hydra, in which multiple robots are building their own scene graph, and then they're communicating with the base station to jointly optimize the scene graphs in a single, globally consistent representation. With Hydra Multi, we're in early stages, I would say. The pipeline is still centralized, so we rely on a central computer. But there are cool things in which we exploit essentially the hierarchical structure of the scene graph. For example, we define hierarchical descriptors for loop closure detection, and we use these descriptors to match pieces of the trajectory across different robots. And again, we have robustness to outliers using rather than non-convexity. So I was motivating at a high level the need for metric semantic and 3D scene graph representations. The question is, are they actually useful in practice? And in this slide, I'm arguing that the community is realizing more and more that scene graphs are likely to be a good representation for a number of high-level tasks in robotics. So the three works at the top of this slide are showing that with scene graph, you can start doing more efficient path planning through the hierarchy of the scene graph. You can use the scene graph for reinforcement learning-based object search and get a boost in performance. And you can also use scene graph to reduce multi-robot communication. More interesting, so the top ones are work from my group. More interesting, the work at the bottom are works from other groups, also seeing that there is an advantage in using these representations. For example, there is a choral work on task planning, it is called taskography, using 3D scene graphs. And there are more recent work on both task planning as well as goal navigation, showing that scene graphs are a good representation for these tasks. There is much more. I believe there is much more to be done on task and motion planning, human-robot interaction, visual Q&A, monitoring prediction, and so on. So hopefully in part one, I convince you that we have to move from SLAM to metric semantic mapping, and 3D scene graphs are a good representation to think about the future of mapping. In part two, which I will keep in 3 slides, I'm going to talk about robustness instead. Okay, so this is a summary in 3 slides of maybe 6 years of work of my group. I'm going to talk about certifiable algorithms for robot perception. So what is the context here? The context is that in the previous part where we built scene graph, in the back ends of these nice videos that I'm showing, at the end of the day, we're solving just a bunch of estimation problems. For example, we are solving estimation problems in figuring out the pose of objects from sensor data, or we are solving estimation problems in reconstructing the trajectory of the robot as in SLAM. The nice thing is that despite the diversity of these perception problems, object estimation from point clouds, object estimation from images or SLAM, at the end of the day, these estimation problems can be thought of as an optimization problem. In this optimization problem, we're trying to estimate the variable X. For example, let's think about this as the pose estimate of the object you want to localize. And we are given measurements yi, which can be understood as maybe detection of key points in the image. And we want to compute the X by minimizing a residual error, which is measuring how well given estimate is explaining the measurements. And of course, we have a large set of measurements M. So in practice, the roadblock is that many of these measurements are largely incorrect. They are outliers. Okay, for example, if you want to do a pose estimation, object pose estimation, we want to approach a pose estimation problem, some of the key points we detect might be correct, might belong to the object. Some others might be outliers and might be completely wrong. Therefore, we have to figure out how to estimate X in a way that is robust to these outliers. Well, you might say people in robust estimation, 60 years ago, they already told us how to solve this problem. They told us we just have to add a robust loss function in front of our optimization problem. In my case, this is the raw function. What people in robust estimation didn't tell us is how to solve the corresponding optimization problem. And indeed, has been known for a while that for typical choices of raw, this problem is probably hard to solve. You cannot solve it in polynomial time. Just to trivialize the state of the art in robotics and computer vision, the typical approaches to solve this problem are either local solvers, think about gradient descent, which are essentially starting from an initial guess and going downhill. Well, in many cases, we do not have an initial guess, and also it is known that these approaches are easily stuck in local minima. The alternative in computer vision is RANSAC, which is a very elegant algorithm, but for those of you who are familiar with RANSAC, that will essentially apply to low-dimensional problems, will not apply to things like SLAM. And in both cases, these type of approaches will just fail without notice. They will give an estimate for the X. The estimate can be completely wrong, but they will not be able to tell you that the estimate is wrong. So over the last several years, we have been pushing on this idea of certifiable algorithms. The idea of certifiable algorithm is very simple. Certifiable algorithm is one that computes an estimate and either certifies that the estimate is the optimal one, is the best you can get, or otherwise is able to detect a failure. Okay? So again, we want to solve some optimization problem, which returns a robust estimate. Either we solve it and we provide guarantees that we solve it correctly, or we declare failure. We've been working on these topics for a number of years. The truth is that rather than having a single algorithm at this point, we have a toolbox of algorithms. And I can summarize the set of algorithms we developed in 3 classes. There are algorithms based on graph theory, which are pruning outliers, are just detecting and isolating outliers. There are algorithms based on graduated non-convexity, which are providing a heuristic to solve this optimization problem properly. And the last set, which is the one I'm most excited about, is the work on semi-dynamic moment relaxations, which can provide optimality guarantees on the result of this robust estimation problem. Of course, I will not have time to enter into the technical details here, but as output of this research line, essentially we have the first algorithms for robust estimation in robotics that can compute provably optimal estimates. So just to give a flavor of what is the practical impact of figuring out this robust estimation problem, I'm summarizing in this slide the type of results we get in 3 problems. Object pose estimation in point clouds, the problem over there. Object pose and shape estimation in the middle, and robust pose graph optimization. For estimation from point clouds, we developed teaser++, which is an algorithm for pose estimation robust to 95% random outliers. 95% means I give you 100 measurements, 95 of them are complete garbage. The algorithm is still able to figure out the 5 correct measurements, and it's running in real time. The other one is a little bit more. Not only is estimating the pose of the object, it is also looking at the shape of the object. Much harder problem, so the robustness goes down to 70 to 90%, but still great robustness to outliers. And finally, robust pose graph optimization, in which you have robustness to 70, 90% of outliers. And this algorithm is working pretty well. Indeed, MATLAB decided to include it in its navigation toolbox. It is also part of GTSAM. So if you are doing SLAM, if you have problems with outliers in the loop closure detection, try Gaussian non-convexity, and robust pose graph optimization is a pretty robust algorithm at this point. Okay, so for the last part, I have around 30 seconds. I want to tell you about going beyond human annotated data sets and thinking about self-supervised object perception. The truth is that I will not tell you about the technical contribution. I will tease you about what the contribution is about. So in the previous part of the talk, I argued that right now we have very effective algorithms that, going from measurements, for example, key point detections, will figure out a robust estimate, for example, a robust estimate of the pose of the vehicle in this case. In practice, these detections are produced by a neural network. There is a neural network which is figuring out semantic features of the car in this case, and this is what is called the perception front end. So the question that we've been asking in a bunch of recent papers, including a TRO paper and a recent RSS, is now that we have certifiable algorithms to solve the back-end estimation, can we use them to self-supervise the neural network at the front end? Instead of just manually annotating data and learning from training data, can we use the estimation algorithms to provide a supervisory signal to the neural network? And in the TRO paper and RSS 2023 paper, we have pretty compelling results showing that you can learn for object pose estimation, you can learn from real data without supervision. Again, no time to get into the technical details, but these 2 papers are the main ones describing this line of work. The thing I'm excited about is that, so far we've been thinking about maybe object detection. I've been describing how to go from images to features to robust estimates. The same idea applies to object detection in point cloud. The same idea applies to SLAM, right? There is a front end and there is a back end. Now that you have very good tools for the back end estimation, how do we self-supervise whatever is coming in the front end? So I think there is a lot of research to be done in this area. So I'm running out of time, so we'll conclude here, summarizing the 3 main takeaway points of my talk. Again, we'll be pushing the state of the art, trying to push the state of the art in these 3 directions: robust and scalability and high-level scene understanding. And our main conclusions is that the next generation robot perception requires metric semantic hierarchical maps and, of course, real-time algorithms to estimate them. The second conclusion is that safety critical application will require certifiable algorithms that are able to distinguish correct estimates from incorrect ones. And the last point is that once we have certifiable algorithms that are able to distinguish correct estimates from incorrect ones, we can use that information to enable self-supervised learning, and we can learn without supervision. That's the time I have. I will thank the sponsors, and I will thank you for your attention. I'll be happy to take questions.
Hi, excuse me. So currently I get the news from ICCV, so all the people should exactly cannot stand in the meeting room and should be able to sit. Because if you violate this rule, and you have to be out. So I recommend you to just directly sit, because I just get this information. So people stand here, sit here. Could you please sit on our seats? I just for a couple of minutes. Okay, so
okay.
Yeah.
Thanks. Yeah, I think we had a couple of questions.
Yeah, it's a very hot topics, and yeah, thanks for cooperation. Yeah. Okay. Okay. So maybe we can start. Okay. Can you still take the questions?
Yeah.
Okay.
So you guys have questions? Go ahead.
Yeah.
So for the only answer to probably work
Yeah, so there are two flavors here. There is the version without outliers, and there is the version with outliers. Without outliers, actually the semi-definite relaxation will have a very fast solution, which you might know about, which is SC-sync, which is as fast as GTSM. Like, so you get global optimality without extra computational effort. For the case with outliers, the problem is much harder, and unfortunately, we don't satisfy technical requirements for Buer and Montero, so it is not feasible. We do not have a very fast solver in that case. So for the SLAM part, like the moment relaxation, at this point is more of theoretical interest because it's the first approach to certify global optimality. It's not something that you can run in real time on a robot. Great question.
The third question is, in terms of the species, genetic graph, have you ever seen the large language model actually could be a sweet spot in the future, and probably we'll see in the next couple of years how this kind of going to shape.
Yeah, that's a great question. I was chatting about that a little bit more at the scene graph representation workshop yesterday. There is a huge role for language for scene graphs. And at one level, for example, if I had to redo this chimera from scratch, instead of doing the traditional semantic segmentation, I would use clip feature for the mesh representation to open set. So you have seen works like concept fusion, for example. There are recent works which are doing the mesh reconstruction or the low-level metric semantic map using language embeddings instead of just fixed semantic classes. I think that's a great idea. Fixed semantic classes will not be generalizable enough. And there is also another role for language, which is to enable zero-shot classification at the top layers of the scene graph. Maurice was mentioning something about that in his talk. But essentially, we also have words in which, given the objects in a room, we can use language to classify the type of room the robot is moving in without relying on training data. So yeah, language can be very, very useful. Yeah.
Okay.
Thank you.
Original presentation. Now let's
Hi, Professor. Are you here?
Hello, I can hear you. Can I share screen now? Hello?
Hi, Professor Ji Zhang, can you hear us? Could you
I can
please
hear
share
you.
screen?
I can hear you. Hello? Can you hear me?
We cannot hear you. I think you are muted, Professor Ji Zhang.
No, I have two computers.
Could you?
I have two computers.
No, we still cannot hear you. You are also muted. In your Zoom. So, oh, okay. So can you speak?
Hello? Hello? Can you hear me?
I think the voice is too low. The sound is too low. So, oh, okay. So can you speak?
Hello?
Hello. Yeah,
Hello?
we can hear you.
Hello?
Yeah, sorry. Yeah. Okay. Okay. So Professor Ji Zhang, can you share your screen?
Yeah.
Okay, cool. Thanks.
Can you see my screen?
Yeah, great. Yeah, we can see.
Thank you.
Yeah. Thanks.
Okay, can I begin?
Yeah, I think you can start. Yeah.
Okay. So we'll be talking about autonomy system today. We are providing the system to everybody. Okay. So the work started from SLAM several years ago, and we worked on LiDAR SLAM. And this is what we got in 2015. This is where we started. We worked on something called LOM, LiDAR odometry and mapping. So that's a 3D LiDAR on top of my head. That's myself jumping over that electrical vehicle. And there's an IMU inside the 3D LiDAR. We were able to process the data, estimate the trajectory, and building a coherent point cloud map of the environment. This is the final point cloud from that SLAM algorithm, and this is manually labeled just to show the accuracy of the scan registration. So we were able to do this in 2015. And from there, we wanted to move on to autonomy. We only had SLAM, but what we did was connecting SLAM to a flight controller or a path follower, and we put it on a drone, and we were able to fly it autonomously. Right? So this is that drone flying. It's not a full autonomous system. It's just following manually defined waypoints, but it's flying autonomously. Okay, so in that sense, so that's me again. So in that sense, this is an autonomous system just by connecting SLAM to a path following flight controller. And we got our first step into autonomy. Okay. And it really got us on the road to develop the autonomy system. Okay. So this is where we started. And it got us on the road to develop this autonomy system over the last few years. We started from SLAM, and our SLAM kept developing. And today we are calling it super odometry. Shibo will be talking about it this afternoon. So Shibo is the organizer. Please check it out. And we are going to focus more on the autonomy side of the system. So on top of SLAM, we build up multiple layers. So we first have this mid layer with 3 modules. They are all fundamental navigation modules. The mid layer is meant to be providing the fundamental navigation functions for terrain traversability analysis to analyze the terrain and segment the terrain into traversable and non-traversable. It's just for ground vehicle. Okay. Aerial vehicles don't need to analyze the terrain because aerial vehicles don't touch the terrain. Aerial vehicles only need to know the free space. But ground vehicles, because it's touching the ground, it needs to actively analyze where is traversable and where is not traversable. That's what we call terrain traversability analysis to segment the terrain. Okay, clear avoidance to plan passes, local passes in front of the vehicle, and to guide the vehicle through obstacles, nudging the passes in front of vehicle to make sure the vehicle does not hit anything. So that's basically what clear avoidance does. And pass volume control. Okay. Well, we had these three modules, and on top of it, we start to build. And on top of it, we start to build this top level, this high level modules. So modules at the high level, they are targeted at particular applications or missions. So here we're listing two. We have exploration and route planning. The exploration is to send the robot into the environment and it goes to everywhere. In the end, it builds a full map of the environment. That's what we call exploration. And route planning sends the robot to a goal point or multiple goal points. So if you look at these two planners, they are from two main classes of navigation problems. The exploration, we say, it's from the class of problem called coverage. We send the robot in, it goes to everywhere and builds a map. So it's covering the environment. And the route planning, it's sending the robot to a sequence of goal points or just a single goal point for something like a delivery, to go somewhere to deliver something. Okay. So that's the overall structure of our SLAM system. And we have this system, it's open source, we're providing it to everybody. What we're doing here is to support everybody's work. And we want to use it to support advanced AI. If you work on the advanced AI, you're most likely working on the high level in the system because AI is at the high level, and you don't necessarily have to spend time to build the base navigation system. That's what we are providing here, where we don't expect everybody to be able to build the system from scratch and for all the parts. If you're focusing on the high level part, the AI part, you can utilize the space navigation system from us because it's our specialty. Okay. And why are we doing this? So I would put something in called technology readiness level, TRL levels. So this is a chart with 9 levels, and we use it to evaluate how ready a technology is to be used in users' hand. The bottom part, the orange part, we call it fundamental research, proof of concept in the lab. The middle one, in light blue, this is getting interesting. The technology goes out of the lab and being evaluated in the field. The dark blue, we usually think of it as stepping into the industry and getting into the user's hand. Okay. So what we are looking at here are these two levels, the level 6 and the level 7. So this is the step that getting out of the door of universities and getting into the industry. So let's read these two levels. So level 6 says, technology demonstrated in relevant environment. So if you don't evaluate your technology in the exact operational environment, if you don't have that condition, or if you don't want to do it, you can evaluate your technology in a relevant environment that looks similar to the real operational environment. And by doing that, you're at level 6, okay? But if you do evaluate your technology in the operational environment, you're level 7, you're 1 level up. So what's the difference here? The difference really is the testing environment. It could be the same technology and same prototype. These 2 levels, they don't distinguish the technology or the prototype. As long as you operate in the operational environment, you're level 7. So what we're doing here, back to our story, we are essentially providing this space navigation system with the fundamental navigation capabilities to assist everybody's work, to help you realize your technology in the real environment on the real platforms, and pushing your technologies up level by level through this chart, and eventually getting into the dark blue part, into users' hands. Okay. So next, I'm going to use 2 slides to show 2 high-level functionalities or capabilities. We're showing exploration here as the capability of the system as a whole. And in the next slide, I will use a simulation demo to show the route planning. So we don't have the time to go through all the details in the system modules. We have a few backup slides in the back. If you are interested, you can download the slide deck and you can look at it, or all the information is on our website. We will give out the web link in the end. So here, this is the exploration. It's one of the 2 main functions of the system as a whole. The vehicle goes into this environment and it explores. Our system works in simulation and it works on real platform. This is our own real platform. It's a wheelchair-based vehicle. We bought the wheelchair, we retrofitted, make it a drive-by-wire, and we build our own. So this shows the planning, the exploration planning. It's constantly replanning the blue paths to guide the vehicle through the environment and to explore. The on top of the robot is the 3D LiDAR from Velodyne. And there is IMU in the blue box. There is the i7 processing computer in the blue box. All the processing is happening on that computer in the blue box. And now this is after exploring the garage that got onto a patio connected to the garage. Here we're showing the local planner widest. Okay. And this is covering the other side of the patio, and this is to the end of the exploration route. Okay. Now we are seeing the whole exploration process, starting from the top of the garage, going level by level to the bottom. Here is the bottom. And now it's circulating back to the top of the garage. And it's getting to the patio right now. Here is the patio. And it's returning back to the front. Here is the component map review with the vehicle trajectory. All the processing is happening on the computer in the blue box. And by the end of the run, we have this console. And this is with our student application system. And our okay, for now, I want to switch to my other computer to show a simulation demo. So, this is demonstrating the other capability, which is to to the goal point. Okay. We call it route planning or goal point navigation. So this is our navigation system running in simulation. We're looking at this left part. This is about the navigation and the planning. The right part, these three images are rendered by the engine. It's called AI Habitat Engine. And we're using a environment model from Matterport 3D as open source model. So here, I can give a goal point to the system, and it's planning the path. The system can start in unknown environment, knowing nothing about the environmental layout. It figures out its way as it moves around. It keeps looking for the better path, and it builds up its own graph. The blue path is the global path from the route planner. Red and green are from the visibility graph, which is our global route planner. Okay. So it's trying out a few ways. It's getting into dead ends, which it doesn't know, but once it figures out, it corrects itself by replanning and guiding itself to the goal point eventually. Okay. Okay, at this point, it has got to the goal point, and I can give another goal point here, and it will keep planning. If it does not know the environment, if it's going to a new environment, it replans and it figure out the way on the fly. But if it's going to somewhere that it has been to, it will figure out the way immediately. Because this part has the graph coverage now, and it does now needs to fly and to figure out the environmental layout. Okay, so that's the navigation to the goal point by our global route planner. Now there's another feature in the system, which is to use a joystick to drive the vehicle. We call it smart joystick. Now I am going to push this button to this joystick to teleoperate it, and this is directly interfacing with the local planner, the local clear avoidance module in the system. You can give it a rough direction. Okay, you can give it a rough direction and push the joystick. It figures out the clear-free way to go. Okay, so this is the cooperation between your input through the joystick and the clear avoidance module. It's trying to follow your command, but it's also making sure it's not running into anything. Okay, so we found this to be useful feature for debugging and for some of the applications actually. And if you want to resume the navigation to the goal point, you can click here, resume navigation to go, but it will go into the original goal point, or you can give it a new goal point. Or you can use this virtual joystick, which is the same with this one. These two are the same. So you can teleoperate it here. If you don't have a physical joystick, you can use this virtual joystick to try out our system. Okay. Okay. Now I will switch back to my slides. Okay, this is the route planning. We saw the simulation demo. And here I will quickly talk about how to use our system. Okay, we support multiple open source LiDAR SLAM approaches. They are open source. We support all these listed here and more. Our own LiDAR module is called Super Odometry. It will get released in the next few months, and by the time that it gets released, it will support the system, of course. And do check it out and use it. We support multiple types of platforms. Okay, there are all kinds of platforms out there. We support by default the differential drive platforms, which is the top row here. That's what we support. The second row are the omnidirectional wheels. Omnidirectional platforms, including the Lego robot. So these platforms, they can go sideways. Our system supports it, but it does not fully utilize the fact that it can go sideways. It still tries to drive it forward and turns the vehicle and drives to another direction. But they are supported. So omnidirectional platforms are supported. The third one is a little bit problematic. The car-like vehicles with steering wheels, that's the one on the bottom. So for these vehicles, we only partially support it because we only support one-way drive. The car-like vehicles, if you drive it into a tight space, every once in a while, it needs to back itself and to turn in another direction. So we call it three-point turns. Our system does not support three-point turns by default, and supporting it needs some modification to the code. It's possible, but by default, the open source version does not support three-point turns or the car-like platforms fully. Okay. So our whole system is open source. We're listing the web link on the top, cmu-exploration.com. A good number of users are trying it out. And we got all these pictures from our users. When they ask us questions, they send us a picture to tell us what they're doing every once in a while, and we collected this. All these pictures, and you can really see that all these users, they're trying many different things with our system. And if you look at this, one on the bottom, in the middle, and on the bottom, it looks like two military vehicles driving in a vineyard. I will very quickly show 3 use cases, just 3 topics. Everybody here using our system has a better idea of how to use it to facilitate your work. We're just giving 3 example topics. So first one is social navigation. You can insert human avatars into the system and to try developing your algorithm that drives around people walking around. Next, initiative navigation with human interactions. You would develop a module that interacts with people through languages. The robot asks the person a question, how can I get to somewhere? And the module listens to the command or the directions from the person and interprets the language, and it uses our base navigation system to navigate and to avoid collision. Okay. And another popular topic, sim to real navigation, bridging the sim to real gap. You would upgrade the simulator in our system to a more realistic simulator, or replace the environment model in it by a model that matches your testing environment. And from there, you can develop your own algorithm or your models in the simulation using all the navigation functions in the system. And eventually, you can put it on your real robot and test it in your real environment and see how it works. Okay. So in the end, our system has been used in Dark Submarine Challenge. A couple of years ago, we had the final, and our team was the one that made the most complete exploration in the final. Among all the teams, we made the most complete map, and which is the map here, made by 3 robots. The 3 trajectories here, the red, green, and blue, are from the three robots, and this really shows the strength of our system. It's a working and a reliable system, and now it's made available to you to use to facilitate your work. Okay. Some papers, if you are interested in the technical details in the system, you can look at these papers. But if you just need to use the system as a tool to facilitate your work. You don't necessarily have to read these papers. The system is made easy enough for you to use as a tool. And that's all. Okay. And please give it a try and see if you can use the system to help your work. Okay, thank you. Any question?
Hello. We can't hear it.
Can you hear us? Better now? Can you hear us now?
Yes, it's better. Thank you. Yeah.
Okay, so oops, that's not the one. Okay, so essentially I'll start really from long ago. So I said I'll go from classical to then modern approaches, and also see how in application structural motion and SLAM are really closely connected. This is very long ago. This was essentially the first system that really combined, that went from images all the way to dense 3D models, as you can see here. Here's another example of that, starting from a video sequence and then going, oops, doing search for motion, computing the trajectory, and then from that go all the way to 3D models as the one you see up here. So this is long before NERF and so on, we could get kind of quite accurate, detailed three-dimensional reconstructions from images. This was about 20 years ago. We were mostly working on images that were very carefully taken one after the other, or video sequences, because we couldn't really match between images. Once SIFT came about, that actually really changed things. People started doing photo collections, as the few works you see here. You could match images that you didn't have to be a computer vision person and understand what algorithms and matches could do. You could actually work with quite unrestricted images. Here's a few example. One of my student Chang Wu, who then continued at UW and built Visual SFM over the years, and this became one of the standard pipelines for search for motion. We continued trying to make this a lot faster, do things like this, scale this up further to really large scale collections. And that in a sense then all converged into Colmap, which today is often used as a reference pipeline to figure out how images, sensor data essentially relates to each other, and then also enables dense multi-view reconstruction also on top of that. One of the key applications often in systems where you have an environment, you need to map the environment, you need to localize in the environment. Those questions, SLAM, you do all of it together. There's many scenarios where you might do first one and then use the other, and it's a space that you're not, like in an emergency scenario, discover once and then and have to map it at the same time and do all of this the best you can in a simultaneous joint problem. There's many scenarios where you can actually afford, you map at some point in time, maybe you'll update the map and so on at later times and so on, but most of the time you're actually just using it in localization mode. Typical pipeline up here is an example of some work that with Thorsten. I saw Thorsten here, and Bernard Seissel was a PhD student working on this, doing localization by voting. Features would vote on where they might have been seen from, and is allowed to actually scale very nicely, and also became, as Bernard moved to Google, became actually the base, the starting algorithm for the street map navigation. Here's an example of something we've been working on more recently, but using a lot of these classical techniques. Essentially, you walk around with a device like the HoloLens. The key value is to be able to access, get questions answered about questions about the environment, know what's in front of you, being able to have, let's say, a digital representation of the environment aligned to the real world, and be able to visualize that. How do you build those maps? Many different ways, but one of them is really just by walking around. So essentially really SLAM. But then when you combine SLAM with then puzzling, you have on-device SLAM, you combine that with cloud, the data from the device gets pushed to the cloud. As multiple people walk around, this data comes, all comes together in the cloud. In the cloud, in a sense, you're really puzzling all of this back together and then optimizing, of course. So that's what you see here. You can have not only people, but also other agents that have cameras and sensors can all come together. And here you see some examples of how of this can all come together. You have also depth data, or you do multi-view stereo and so on. You can also extract different layers. And here's a few examples of the type of representations you can build up. And so you get a kind of SLAM system in the cloud that also has on-device SLAM systems all work together in building these larger representations. Here's an example of then using this at scale in a factory setting to support frontline workers, so people that are in the real world, working with their hands, trying to solve problems, in the real world, and so maybe get assistance from someone remote. So here's an example of how these maps kind of come together at that scale. Here you see all the trajectories. Means we can also support actually people navigating people through those environments. If we know where different points of interest are, you localize in one location, you can be navigated to the other location. This is a space of about 100 by 100 meters roughly. The map was obtained by just walking around with the device like the HoloLens, or with HoloLenses. And then all of this, being moved to the cloud and optimized, and you get these type of large scale models just coming out of them. Okay, so let me now switch gears to some modern techniques, some more recent leveraging deep learning, leveraging the fact that we don't have to hand tune a lot of things. We can actually, from data, leverage a lot of data to fit functions that will actually do the right input-output behavior based on just showing a lot of examples and learning from that. Or also bootstrapping from one task to another task. In this case, this was our D2 network, which essentially was leveraging a semantic network to then do both detection and description of features. So instead of having those in two separate stages, like in SIFT, you have difference of Gaussian kind of detection, and then you have a whole descriptor on top of that that looks at gradients and so on. In this case, it's actually the same network that both you find maxima in that network of responses in particular channels in that network, and then you actually use the response in all the different channels as a descriptor. So same network for both purposes. This works very well across wide changes of viewpoints and across, because of the more semantic kind of, also across change of illuminations that you see, day-night type of scenarios and so on. The downside is that the localization was less accurate, which is typically is with those more semantically inspired networks. What we then did was look at, could we do better? Because once we match, so there's a big difference typically between tracking and matching in structural motion in these type of problems or in SLAM. As long as you track, you can really, you have a specific template and you look back the exact location of that template as it moved in the next frame or so. If you do extraction, you extract independently and then you match. And so you might actually extract a slightly different point that still, can be matched, but you might not have exactly the same very precise location. So the idea was, once we have extracted in both images and we know those two are matching, can we refine the location knowing, how the other, patch locally looks like? Can we do a refinement step? Okay, and so we bring that in structural motion. It's actually a very easy step to insert in a structural motion pipeline, as you see up here. We actually also later revisited that with slightly different concepts. We also looked at the possibility to learn the features directly for the purpose of relocalization. Okay, so in this case, at some level, we assumed we had already a 3D point reconstruction, but we wanted to learn features and multi-level features that would be helpful for relocalization purposes. And so the goal was actually to put that in a backpropagation framework, and now just train the features that will do best at relocalizing and allow us to do a gradient descent locally at different scales to the proper localization. It kind of works like this here. You start from the closest image, so you assume that you have a way to find the promising nearby images, and then you essentially have these gradient descent steps that will essentially refine and try to align this kind of feature metric representation, align these feature response as best as possible to each other, and in a few steps you essentially get a localization. The nice thing is, by learning this, we not only learn these features, but we actually also learn the confidence of these features. So as we extract features, we essentially determine, is this feature that we just extracted, is it a useful feature? Is it a feature we should actually rely upon? Or is it a feature that maybe we should ignore because we know it's kind of ambiguous, we know it's not very useful for the purpose of localization, because we trained it in, on a localization setting. Okay, so what you can see here is that it actually figured out that cars are not very useful for localization. The algorithm figured it out. We didn't have to tell it anything or say ignore cars or something like that. It just learned that things that look like cars are pretty useless for localization, because of course those cars tend to move and appear in different places at different times. As you do the localization problem, they turn out to be useless for localization, and so the system just learns to ignore those very nicely. Also here you see at the finer scale, it learned to ignore these very fine repeating structures like bricks, which are also blue, and so kind of are low, are weighted low in terms of provenance, is because they can very easily get confused between those features, and so it kind of learned to ignore. So here also we actually use this system to then do auto refinement step in structural motion, very much inspired by also the previous work you just saw. Then in terms of matching, this is actually work that will be here at the conference. So there's more work by Philip Lindenberger, who's one of my students, who's here in the audience also, and Paul-Edouard Sarlin, who's also somewhere there. So light glue is essentially, many of you might know about super glue, which is using super points, and on top of that super glue to actually try to really refine and find and have these kind of self-attention and cross-attention mechanisms to determine a good set of promising matches on which you can still do ransack afterwards, but have a much better set of matches between a pair of images. You see that here with light glue, we can actually outperform all of the existing methods. And in particular, a really nice concept here is that we do this multi-stage, multi-layer, refinement of these self and cross-attention steps. We can do these multiple layers. We do it up to 9 layers, I think. And you can actually learn to abort early. If it's an easy problem, as the one you see on top here, you can actually do a few steps and then say, okay, I'm good, I converge, I'm good enough. I don't need to do more effort. And then when it turns out to be a really difficult pair, where the images are much further apart, much bigger scale difference or something like this, you need to iterate a few more times to get to a solid set of matches between the two images. That's fine. It just does a bit more work. On average, on a large collection, this can make a huge difference in average speed. Of course, here's a few more examples of light glue at work. And as I said, you'll get all the details by going to the presentation of Philip, to Professor Philip and one area I won't have the time to go into is we've done a lot of work as you do these kind of settings where you do mapping and then other people might use your maps and so on. It's also important, or also you are submitting queries to the cloud, for example, these type of scenarios, you're submitting the equivalent of images to the cloud. Starting to ask the questions, how much information are we actually sharing? And how much information, is there maybe some information we would not like to share? Do we have options to still get localized, for example, if that's what we're trying to do as a task, but at the same time, not share information that we might be concerned about in terms of privacy. So lots of different work here. The key idea was to say, well, for localization, we kind of need some localization constraints. But when we get a point localization, a 2D point or a 3D point, we have already more than one constraint. Typically, essentially, having a 2D, 3D correspondences gives us 2 constraints at a time. The key idea was, okay, what we'd actually do is we drop one of those constraints. So we only get 1 constraint per point instead of 2 constraints per point, but that's still enough. If we get more points, it's still enough to localize. But that way we share a representation that's not anymore easily interpretable. It reveals a lot less information. You can do the typical reconstruction attacks don't work. We have these line clouds and 2D and 3D line clouds, depending on what setting you have and what privacy you want to preserve and so on. We build a whole structural motion pipeline and some kind of system in this context. We also apply the same concept in feature space, where also there, instead of having a point vector in a high dimensional feature space, we can actually relax that to an ambiguous linear subspace in the feature space. And what still allows matching, a little bit degraded, but allows matching, but reveals a lot less about what, the details of what was actually visible in the image and so on. And so most recently, we have work also here by Limfei Pan, who's the first author on the work on the bottom here, that is also preserving localization and actually can counter some of the attacks that Thorsten here did on some of our earlier work, and so has some very nice advantages compared to the previous techniques. And again, you'll get all the details at the presentation. Okay, so now let me switch to mostly in structural motion and SLAM. People have mostly focused on point features. For good reason, they're easy to work with, you get 2 constraints at a time, and so on. But there's also many scenarios where if we're in an environment like this one, if I look around, I see a lot of strong line features, that are very stable. But and very few point features that would be stable. So we think that in especially indoor human-made environments, we kind of really underutilizing the potential of lines. Now we're not the first ones to think that. So lots of people have tried to use lines. It's always very difficult. There's a number of reasons for that geometrically in terms of conditioning and so on. You get less information. For example, from two images, there's strictly no constraints. If you have a random set of lines in one image, a random set of lines in the other image, you make random associations between them. You can all back project them and you get some 3D lines reconstructed. There's just no constraint, right? In two views with points, you have the epipolar geometry that constrains how points can be located, with respect to each other. So there is some internal consistency constraints available. This just doesn't exist for lines. Okay, so lines are much harder to use in a sense, but if you use them properly and you do everything right, they're actually super, super useful. So here's some examples showing you also just with a few lines to capture immediately a lot more work here. So I'll very briefly talk about a few different work in the line space. Actually, I think I'll mostly skip it, but essentially there's very nice work by Rémi Potra on detecting and describing lines, and then really nice work by Xiaoyi Liu on actually using those lines in a structural motion context and getting very nice reconstruction there. So I'll kind of skip through this here. Also, so detecting lines, extracting lines, describing lines, matching lines. I mentioned light glue before, and super glue here, essentially, glue stick is specifically looking at points and lines in that same context of matching them, both the points and the lines, also in an efficient way. Here, kind of showing you how that's being tracked, how the lines are being matched, essentially matched between the image on the left and the image on the right. Showing you also that many of those are much more stable than typical point features. Then limap is essentially think of colmap, but for lines. It can both combine points and lines actually, but really focus on the line reconstructions. Here's on some of the tanks and temples data, I think. Seeing that with relatively sparse set of lines, you actually already capture a lot of the structure, and you can do pretty nice reconstruction. That was ETH3D data. So here are a few more examples and applications for using lines, and a few work in progress to kind of continue extending and bringing more structure in and solve more general problems. I wanted to finish with also highlighting this new benchmark, the Lamar benchmark, where we're really pushing, we can try to capture a lot of data over different times of day, different seasons. It's both indoor and outdoor data. For now, we have these three large sites, two at the university with some indoor and outdoor settings, and then also part of downtown Zurich, kind of with cobblestone streets. We captured both AR headsets and phones, but in AR type of settings. So not single picture at a time, which we think is very artificial localization from a single picture, but more you are actually going through an experience and you want to localize. Capture lots of different data, so multi-camera rig, when you have a device that has more than one image, RGB, depth, radio signals, all of these things, and new data. We also collected ground truth data then with high-end scanners, brought all of this together, lots of effort here being done in the group to realize this. Actually, it's a collaboration between Microsoft and ETH at this point, but we're also looking at bringing additional partners on board to build out this data set further. So here you see many of those examples. All of those dots are essentially different trajectories localized in those environments. By the way, the people that really drove this at this point are Paul Edouard, Fabin, and Mihai Dusmanu. Here you see large temporal extents, so different times of day. Also, you see here different settings in the environment, construction sites, etc., etc. This shows the accuracy. So we really have most of the data, almost all the data is within a centimeter accurately localized with respect to the ground truth maps. And just showing you a little bit of this ground truth at scale. It's all with depth. So we've aligned it to accurate depth, have the normals, all of this data. And so all of this data is being made available also for training potentially for different tasks, etc. it kind of showing you the quality of the alignment between the night sessions and the depth and all of those things. So what we really focus on is not the single image scenario, but it's really the scenario where I'm starting experience, I accumulate a stream of data. So I'm kind of moving around and I want to get localized. And so the question that we ask is, how much data do I need to accumulate? How much sensor data do I need to accumulate to be able to have a good localization? So by when do I have enough data to localize accurately? Right? If I just notice this is not the scenario where I'm in front of a landmark, I take a picture of the landmark and I ask what the landmark is, which is a very easy problem. The landmarks are visually very rich, typically are quite unique because they're landmarks, right? So they're quite unique, et cetera, et cetera. Here we're talking, I'm just walking around an environment randomly, looking around and through an experience, a mixed reality experience or so, and I'm just collecting data. And so it might be very ambiguous. I might be looking at a white wall, this type of thing. Okay? But over time, I will accumulate enough evidence to know exactly where I am. That's the scenario we're looking at here. Okay, so here kind of showing how different settings, for example, here including Wi-Fi and radio signals, allow to disambiguate much more quickly, and therefore we need a lot less visual data to solve the problem. But that's kind of how much data, how long a length of sensor data do we need to solve the problem, right? Here, if we threshold it at 10 centimeter, 1 degree accuracy. So remember, ground truth is about 1 centimeter accurate. So we kind of set up the benchmark for visualization at 10 centimeter, as we, believe we can, or ground truth is more than accurate enough to be able to measure that. You have the image setting, and then you have a rig if you have a device like HoloLens, plus radio signals, plus then adding sequential data. These are all the percentages of successful localization within those thresholds that we can achieve. And then, we essentially want to point out that this just single image is a bit of an artificial setting that most people use in other benchmarks. But this benchmark is also not saturated yet. So if you look at how much data would be theoretically localizable, essentially almost all our data should be localizable, and we're still far from actually localizing all of it, even when we use all of the data available. So this is roughly the size of data, so 500 gig of data, 45 hours of captures in many short, few minutes sequences with these captured with these different devices. We're also working at extending that. Okay, so if somebody wants to see the QR code, there you go. But just look for Lamar otherwise, and you'll find it also. Okay. So we're also working on extending this to robot data, like in more emergency scenarios like here. The additional challenge is that instead of being sensors with eye height, now you have sensors at a very different location. So the cross-localization can be quite challenging. So there's just a few examples of recent captures in this kind of emergency business.
Can you maybe look around a bit?
Okay, and then really last slide here is also in all of this, not only geometry, but beyond that, also bringing in semantics is something that, in my group, we've been working on for the last 10 years at least. Here's some of the latest work, which was a collaboration with Google. It was actually a Google internship with Tom Funkhauser and the student, Song Yu Peng, who's actually graduating soon. Doing some really nice work here on essentially using CLIP that connects word embeddings to image embeddings to extend that to connect it to 3D point cloud embeddings. And then when you have a textured 3D model, so from textured 3D models, you can train all of this. And then when you're given a textured 3D model, you can compute embeddings both from the images and from the 3D. Given those embeddings, now you can pre-compute this on the whole 3D model, as you see here. And then when you're given a textual question, a textual description or a question, you can enter that, you generate an embedding, you correlate it with the whole scene, and you see where the strongest response is. You can normalize that as you see here. And then the strongest response is probably the most relevant answer, of a place in the world. That's the part of the environment that's most relevant to address your query, right? And then to finish, for all of you interested in 3D, which as many of you are, I want to kind of remind you, it's too late to submit papers, but definitely not too late to come and attend. And I hope many of you did submit papers. We certainly had the most submissions until now. Davos, March, still, still a month to go in the ski season at that time. There's also good opportunities for students to come for actually very, very cheap. We have a deal with the youth hostel for $60 or so per night, including dinner. So actually very good options for you to come. So if you're interested in this, check it out. And I hope to see you there. And I'll stop there.
Hi, and I have a question about the Minecraft. So like usually in robotics, a lot of applications use fisheye cameras because like would it actually affect the line detection or the constructing the line map?
So certainly at the low level line detection, yes. I mean, you'd really have to be careful of how you kind of run. You'd have to adapt your. I mean, either you'd have to retrain a network that's specifically targeted to those cameras, but you can also do it properly by just rewarping. But you have to be very careful in how you do that in terms of sampling. In general, the fisheye cameras are tend to be kind of equiangular. In that sense, it's not too bad. So you kind of a very wide field of view with a perspective camera has a lot of distortions in the angles. Here, you actually see in every direction you have the same amount of pixels visible at anywhere in the image. If you have a good quality fisheye camera, you have the right data to extract those lines and extract them over, vanishing points. You can, like lines in a hallway, you can now see them from beginning to end in a fisheye camera. So on the one hand, you're much better. The data intrinsically is much better, but at the low level of detection, you would have to do quite some work to make sure you extract, like in the best possible way from the raw image data, because of course it's not straight lines there. All of that can easily be treated with geometry, but you'd have some, dedicated work to adjust the first steps of your networks or do some mapping to do that. But otherwise, those would be great cameras for that. Yeah.
Thank you for sharing such information and now, I'm excited to introduce our next topic.
Hi, hello. Yeah. Are you able to hear me?
Yes.
Okay, so
Yes.
There's that.
Sure.
Okay, yeah, yeah. Okay, hello everyone. My name is Shen Wang. I'm an assistant professor at the University at Buffalo. I'm also leading the spatial AI and robotics lab. So today, my topic will be imperative SLAM and typos library for robot learning. So before I start, I would like to revisit the main method of existing SLAM algorithms. So SLAM normally can be divided to two parts, the front end and the back end. So normally the front end is to interpret sensor data and generate initial pose and map it. Sorry, I hear you are you talking to me? Okay, so then for the backend, it is to generally globally refine the initial estimation to improve the overall accuracy. And normally this is a one-way connection. So right now, most researchers have found that the front end they can use engineering features or deep learning based method. And right now we find that deep learning method has outperformed the traditional geometric method. But for the backend, we find that it is still optimization based, or we call it interpretive optimization. So many people believe that the future of SLAM should combine the deep learning method with geometry-based method. But the question is how? How can we combine them? So before I answer this question, let's first list several properties of deep learning-based method and classic geometry-based method. So first of all, the deep learning method has very strong feature extraction ability, and it is somehow robust. For example, it is robust to elimination and dynamic objects, but it is very data and label intensive. Most of the existing algorithms are supervised learning, which means that they require a large number of labels. For geometry-based method, it is very accurate, especially when correct and significant model are given. But it's somehow not very robust, especially for outliers or illumination. But the good thing is that geometry-based methods, including bone adjustment or post-graph optimization, they are all optimization algorithms. But deep learning is also a kind of optimization. The thing is that geometry-based method, such optimization does not require any labels. For example, when we optimize a factor graph, we don't need any labels. We just use a human-defined loss function to estimate, to optimize the pose. So this means that in the one hand, deep learning is supervised method. It is also optimization. It is very label intensive, but geometry method is unsupervised. So our idea is that can we just take backend optimization as a supervision signal for the front end? In this case, the front end is a neural network, but the backend is unsupervised. So that means if we can do this, that means we will have a self-supervised data-driven SLAM system. And this will also help us to retain the strong feature extractability from the deep learning networks, and as well as the accuracy from the backend. So the idea is like this. So we designed the imperative SLAM framework. That is, we not only have the one-way connection, we also send feedback from the backend to the front end. That means we backpropagate the post graph errors to the front end, so that we hope that it can the front end can learn geometry knowledge from the backend, and it will also result in mutual bias correction and accuracy improvement. And this will also result in self-supervised training without any ground truth label. So to do this, we formulate SLAM, the entire SLAM system, as a bi-level optimization. So specifically for the low-level, bi-level optimization means we have two objective functions. One objective function is subject to another objective function. So in this case, the lower level objective function is just the backend. More specifically, it is post-graph optimization. So it's trying to impose geometric consistency through interpretive optimization. And the high level of objective function is just we attach the front end to the back end, and it processes the sensor data directly. And then we design the geometric-based loss. Here we call it U. So our goal is to backpropagate the error from the human designed geometric errors through the backend to the front end. And we hope this can improve the performance of the front end. Okay, so next thing is how can we solve this problem? Because this is a bi-level optimization. The solution will be very complicated. So many existing solutions are doing this. So to backpropagate the errors of U to the front end, we need the chain rule. So once we write down the equation, we will find that we will need to calculate a very complicated interpretive solution for the optimization. This is because when we backpropagate the errors, because the backend is the interpretive optimization, so we have to backpropagate the errors through multiple iterations, then finally to the front end. So this is very time consuming. But so what we did is that if we assume that the backend can always convert, which means that either it is local minimum or global minimum, the gradient is always 0, which means that this this atom will be 0. And this will result in the one-step back propagation. So in other words, we are using the stationary points of the bilevel optimization to bypass the very complicated interpretive optimization for the back propagation. So until now, we have introduced a basic structure. We have a deep learning based front end and traditional geometry based backend, but we didn't specify any structure. Actually, they can be any existing networks or any existing backend. So here we just use a very simple demo. We design a stereo visual inertial odometry. Because of time, I will not introduce more details about the entire network structure, but I hope you already get our basic idea. So, because of this mutual correction, we can simply perform multiple runs for the forward and backward. Then the performance of the front end estimation can be keep improved. Okay. And next, you may also ask that how can we implement such complicated SLAM system? Because all of them are going to be differentiable and they should work with deep learning based method. So actually our answer is the PyPose library. So next I will play a short video to introduce the PyPose library. Oh, sorry, it seems that there's no sound. Okay, maybe I can reshare my screen and try to play this. Okay, okay. Okay, I will just replay this. Sorry about that.
Introducing PyPose, a library for robot learning with physics-based optimization. PyPose targets for robotics, which mainly consists of 3 tasks: control, planning, and SLAM. Basically, control is to stabilize robot pose, planning is to generate future robot pose, and SLAM is to estimate current or past robot pose. To highlight this uniqueness in robotics, we call ourselves PyPose. PyPose provides various differentiable algorithms and modules for robotics end-to-end training. We also have second-order optimizers, which are faster and stabler. Compared to PyTorch first-order optimizer, our Levenberg-Marquardt second-order optimizer converges in fewer steps with lower loss. You can also use differentiable filters like EKF, UKF, and a particle filter in just a line of code.
So where can I get it?
Simply go pip install PyPose.
Is it everything I need?
We are open source and open for contribution. Add features if you want to. You are welcome to join our community. By integrating differentiable trajectory optimization modules provided by PyPose, we are able to train an end-to-end local path planning network to predict the traversable space and generate physically feasible paths for dog robots. Also, by using differentiable graph optimization and differentiable IMU integrator in PyPose, we trained an uncertainty-aware IMU calibration model, which can reduce the odometry drift dramatically. These can be done with our optimized algebra and Lie group sensors, which enables easier end-to-end training on many robotic tasks. As for SLAM, our modules support LiDAR input as well as camera input. With all of these features together at hand, I believe your unique robot journey with PyPose will be surely easy and pleasant.
Okay.
Introducing PyPose.
Sorry. Okay. So next, you may ask. So I assume that you already know what is PyPose library. But next question you may ask, why do we really need a new library for SLAM? So here to answer this question, here I list several milestone SLAM systems in two timelines. So for the above timeline, it is mainly for traditional geometry-based method. For the lower timeline, it is for mainly for learning-based method. So Shift A is a feature matching, and then we have pioneering SLAM system, including mono SLAM or PTM. Then in 2013, we have Op SLAM, then Long, Wins, and Super Geometry in 2021. So I just list several of them. So and many of you knows that the theory behind SLAM didn't develop so much since the pioneering work of mono SLAM, but Op SLAM might be until now might be the most widely used SLAM system. So what has happened between them? Why there is 7 years gap between them? So after a short investigation, we found that one of the reasons may be that Op SLAM is based on G12, which is a C++ based graph optimization library. And then Long is based on PCL and OpenCV. And PCL was developed in 2011. And then for Wins, it is based on series, was 2015. And then Super Geometry is based on GT4, which was released at 2016. And then we can go to see the learning-based method. You can see that in 2011, we have Super and Super Geometry. They are quite similar to the traditional based method. We call them feature method, so it is quite similar to Shape. And then we have Pixel Lock. We call them handcrafted optimization, because if you read their codes, either mono SLAM or the learning-based method or Pixel Lock or Joy SLAM, if you read their codes, you'll find that their optimization are handcrafted. So this makes them very difficult to be extended for other scenarios. So the engineering or robotics are very difficult to use them. But they are still pioneering work. So to really push the frontier of SLAM, we believe that we need a learning-based library for SLAM. So that's why we develop PyPost, and we hope that maybe in 3 or 5 years later, we can have PyPost-based SLAM system. And we also hope that they can be much more widely used. Okay, and the next, I just list several widely used C++ based optimization libraries. And we can find every widely used method depends on a great open source library. So next is we have choose Python, and I believe many of you will have infinity concern. Why do we choose Python? So to answer this question, I will revisit the history of programming languages for robotics. So about 76 years ago, we have assembly. Then about 50 years ago, we have C, then C++, Python, and Python 3 in 15 years ago. But actually, for in the 1969, the human has able to be landed on the moon with Apollo 11, and those robotics applications was written in assembly. Then in 1994 and in 1991, we have Linux, which was written in C. The Windows 19 Eigen was written in C++, and ROS developed in 2009, which was written in C++ and Python. And until the year of 2011, we have deep learning, and the year of 2016, we have PyTorch. And then in the year of 2021, we have Mars rover, which we know that PyTorch has been able to run on Mars rover. And now the year is 2023. So what will happen? So by seeing this timeline, we can see that robotics tend to use more flexible programming languages over years. And you can see nearly all learning methods are Python-based, or most specifically, they are PyTorch-based. So recall that C++ has a much lower efficiency than assembly, but we still prefer C++ about 20 years ago because it provides more advanced functionalities than assembly. So similarly, so we will keep use the same development tools for robots as 10 years ago in the next 10 years. So if we will have something more advanced tools or libraries, what is it? And our answer to this question in the field of robotics is typos. So another reason that why do we choose Python is that actually typos is not only targeting SLAM, it is targeting the entire field of robotics. So and nearly all perception algorithms models are currently in PyTorch. So compared to control planning, they are more computational expensive. However, the efficiency reduction of classic algorithm may be negligible. If not negligible, we should leverage on the full PyTorch ecosystem for fast deployment. For example, we can leverage PyTorch mobile or TensorRT to do model acceleration. So we believe or we expect that the future of robotics will follow the advanced ML development pipeline. So first we have ideas, then we do fast prototyping, then we iterate this in until we get a good model, then we train it in large scale. After that, we do a model acceleration and then deployment. But right now, most engineering are trying to use C++, then debugging C++. They are quite time consuming. We hope that the robotics can follow the timeline of CV or ML community. For example, they can update their models in every 2 months. Update the state of the model in 2 months, but in robotics until now it is impossible. So we hope we can develop typos to really accelerate this research in robotics. Okay, next is about the users of typos. Actually, typos has attracted increasing number of users. So in this figure, the horizontal timeline, the horizontal axis is the timeline. The vertical axis is the number of downloads by users running page install typos. So you can see that typos has attracted a very stably increasing number of users. So compared to our competitor, the CSys, which is also a Python-based optimization library and developed by Meta Research, you can see that we have totally outperformed CSys, at least in terms of number of users. Okay, next I want to acknowledge all of our more than 80 volunteer developers from more than 20 institutes and 4 continents. And actually, typos library is very big. We still need more developers. So if you are interested in, please join us. And I also want to thank my PhD students, including Kaimon and Xiaoshu. They developed the imperative plan. Okay, guys, all my talk. I will stop sharing. And if you have questions, feel free to ask.
Work actually built a lot of pioneer work for the SLAM. So let's welcome Professor Andrew Davison.
Think it's able to just a previous. Oh, is this a slice?
The screen is not.
Oh, you can mirror screen. Yeah, mirror screen. Display. kind of search this area.
Left.
Oh, left. Okay. Is that here? Mirror. Okay, cool. It's working.
Good. Okay. Excuse me. So I'm going to speak to you today about distributed estimation and learning for robotics, which is something I'm very excited about at the moment. So yeah, we've seen a lot of great talks on SLAM. I've worked in this area for many years, and it's been very exciting to see this technology actually come out into real products. I mean, I think largely so far positioning technology using sparse visual features and sensor integration and so on is quite advanced now, working robustly. And I totally believe in this mission towards building up, capability in layers towards full, we might call it spatial AI, a capability that really enables intelligence in products of the future, with dense mapping and semantic understanding all really playing a part there. So definitely I'm still continuing to work on those kind of things, but I think something I've become very interested in recently is distributed processing. So in particular, we're clearly out of the era where CPUs are just getting faster. We start to use different sorts of compute capability like GPUs more and more in spatial AI and SLAM. But part of the reason I'm interested in distributed processing is that I think this is just the beginning of a path. So we are going to increasingly be designing and using processors that are really built for the sort of workloads we need in SLAM, in spatial AI, and in the future of robotics. And the reasons for that, clearly we can't just run chips faster and faster. We have to accept parallelism. But remember, GPUs are just one way of doing parallelism, and in fact, one quite limited way of running many things at the same, exactly the same thing at the same time. So I think there's going to be a move towards much more sort of heterogeneous parallelism, things like graph-like parallelism. So this is a slide, for instance, from a company called GraphCore in the UK that's developing a new processor they call an IPU. You can think of it as a graph processor with many kind of independent processing tiles on a single chip. They can all run quite different workloads. They can communicate and synchronize with each other via message passing style of algorithms. One great reason to do that might be to drive towards extreme efficiency. So some of the products we might imagine building in the future, like extremely low power eyewear for augmented reality, we're factors of hundreds or thousands away of from the power loads that we really need to run all the sorts of vision that devices like that would need. So a lot of what I've been doing is thinking about, where are the opportunities to match algorithms to hardware? So find the graph-like structures in the data and in the processing we do in spatial AI, and try and map those down onto hardware. And one of the things you're really trying to do is minimize data movement. If possible, we want to co-locate where we store the data and where we do the processing. So we don't want to be moving huge matrices around. That's the thing that's going to cost us power. So there are big improvements we need to find there. I think the other reason I've become really interested in distributed algorithms is thinking about a future of robotics where maybe we have many different sorts of devices trying to interoperate together. And maybe these devices are built by different companies. So this is just an example picture of an application like a smart farm. So maybe there'll be hundreds of different sorts of devices that come together and you want them to really interoperate smartly. How's that going to work? Are they going to all need to somehow talk to some global cloud, probably run by a single company, which might be the extension of current kind of, big tech map-based systems that exist at the moment? Or is there a better, more interesting way to do it, which is more decentralized, where maybe each one of these devices could run its own thing probably obey some kind of public open protocols to talk to each other and to do things like localize together. So let's think about ideas like that. So those things have driven me to think about distributed processing. Now, of course, we know how to solve geometric problems in computer vision, in robotics. You think about them probabilistically. It's the only way that's really been consistently shown to work. And we use formulations like probabilistic factor graphs to really formulate our problems. So, you know, a great review article by Frank Delert, for instance, shows how the same factor graph formulation can formulate a lot of different problems. And interestingly, you know, not just estimation problems, also planning problems. You know, you can formulate a planning problem as a least squares graph of constraints, for instance, and use exactly the same factor graph solver to solve it as you can for an estimation problem like SLAM. Now, of course, there's many different libraries and algorithms out there for doing factor graph inference. I mean, the last talk referred to some of the amazing open source software that's out there, like GTSAM or Ceres, for doing things like this. One thing I would say is a lot of that software is making certain assumptions about computation, and particularly, mostly their CPU algorithms. You know, some of them will take advantage of parallelism and GPU to do certain things. But, you know, that is not the path to be on if we want to move towards, you know, really low power, really distributed systems. We have to think in a different way about computation. So I've been thinking about the sort of algorithms that allow you to do inference on these sorts of factor graphs, but which support distributed inference. And this has driven me back to finding about some older types of algorithms, and especially belief propagation is an algorithm you've probably all heard of. It's developed in the 80s. It's about solving inference problems on probabilistic graphs by passing messages. So all computation is local, and especially Gaussian belief propagation is the sort of belief propagation that applies to exactly the same kind of factor graphs that we're used to using all of the time in SLAM, in planning, you know, least squares, Gaussian type of graphs. So, you know, this is just one of various possible distributed algorithms, of course, but for me, it's very simple. It's very promising. We've tried it on a lot of different empirical things, and it actually works really surprisingly well. And also it has certain guarantees on whether it will converge or not. So in fact, we have an online article. It's called a Visual Introduction to Gaussian Belief Propagation. I think I can just quickly show you this here, which shows you a lot of the properties about this. So you could go straight to this in your browser. It's called gaussianbp.github.io is the web address. So it's built in the style of an interactive article. So it presents, you know, the basic properties of Gaussian belief propagation. So, you know, when you have a factor graph represents a factorizable density. So usually a probability density that can be factorized into a set of terms, each of which depends on just some of the variables. So then Gaussian belief propagation is a way of finding the marginal distributions over those variables, finding the most probable values of the variables by message passing on the factor graph. And there are some quite simple recipes that you have to follow in order to do that. So it's quite simple to implement if you have a factor graph that you understand and you understand the Gaussian potentials. Let me just show you a couple of quick demos of it in action. So the simplest kind of example we could think of was just a one-dimensional height fitting problem. So suppose that you have a set of height observations in one dimension, and you want to fit a set of variables to heights at a set of positions along this one-dimensional space. But as well as the height measurements, you have some other information like smoothness constraints. So you have a factor graph that looks something like this. So here we're going to solve this with belief propagation. If I hit this sweep button here, we're going to pass messages from left to right between the variables, and then we're going to pass messages all the way back. So on this sort of graph, it doesn't contain any cycles. It's just like a line of variables and factors. Actually, just a single sweep left to right and right to left will give us exactly the same marginals that we get via any other factor graph solver. But belief propagation gets more interesting when you look at different computation patterns. So this one, for instance, is simulating a fully parallel computation pattern. So imagine that each of these tiles was living on a separate processor with kind of pairwise peer-to-peer communication, and they pass messages between them. You show that you don't have to iterate that very often to get to the same solution. But even more interesting is what happens if you just pass messages randomly. So here I'm just going to keep clicking this random message button. Every time I do this, a random variable passes a message in a random direction. It still converges. So this is an almost magical property to me of distributed convergence despite ad hoc message schedule. So this works on a lot more complicated problems than just 1D height fitting. Here's a 2D kind of problem that's a little bit like a robot pose graph. I can solve this by synchronous iterations, or I can solve it by random messages, and it still converges. So these problems so far are still linear, but there are things you can do in Gaussian blue propagation. You can deal with nonlinear functions. So with very much exactly the same things as you do in any sort of iterative fact graph solver, you re-linearize the constraints every time you pass messages, and you do that completely locally and dynamically in Gaussian blue propagation. So we can do things like bundle adjustment by re-linearizing. We can also deal with robust factors. So that's by kind of a simple trick that every time you pass a message through a factor and you want to use something like a Huber kernel, you kind of rescale the message to have the same energy as it would do if you pass it through a Huber kernel. So these things are really simple to implement, and they actually work quite well in practice. So certainly have a look at that article if you're interested in more details, but I'm going to go back and show you some other more advanced examples of things that we have done with it. So one is actually to implement bundle adjustment. So this is on GraphCore's IPU. So we implement bundle adjustment by literally taking a bundle adjustment factor graph, mapping it down in parallel onto the tiles of an IPU, and then solving it using message passing and showing that that can be incredibly fast and efficient. So you need more iterations than you would with a standard kind of CPU Levenberg-Marquardt solver or something, but because those are all completely in parallel, it can be incredibly efficient and fast. So next I'm going to talk about multi-robot localization. So this goes back to the picture I showed of the farm, the smart farm at the start. So let's think in particular about this multi-robot localization problem. We've got many devices. They're out there, they're moving around, they all have their own sensors, and they can basically observe each other, and they want to jointly estimate their positions within this space that they're in. So the factor graph for a problem like that looks something like this. So here we're just showing 3 robots. Each robot, we've got variable nodes representing the position of that robot at a series of time steps. We've got odometry factors representing incremental measurements that those robots might make of their motion. And then we've got inter-robot observation factors. So here, for instance, the red robot has made a measurement of the green robot at some time step. And here, both of these 2 robots have made measurements of each other at this particular time step. So to solve this in a distributed way with Gaussian belief propagation, basically we carve up this fact graph, and each of the robots stores a fragment of it. So the green robot stores the part of the fact graph within this green dotted line, within its own CPU style memory. Within that memory, it passes messages around as usual. Whenever it needs to pass messages across to other robots, though, that requires communication. But because the communication can be asynchronous, all it needs to do is to present all of its latest outgoing messages in the form of something like a web page. So think about all of these lines that cross this green dotted line. All of those represent information that has to go out, outgoing messages. This robot just needs to publish something like a table. These are all my latest outgoing messages. And whenever robots are moving around and get close enough to each other within ad hoc Wi-Fi, for instance, they can just read each other's latest outgoing robot web messages, incorporate them into their own fragments, and just keep iterating. And remarkably, the whole thing can still converge. So we call this method robot web, because this sort of idea of using ad hoc web pages, and this is perhaps where this real kind of long-term vision of interoperability and something like maybe an HTML, HTTP sort of standard for multi-robot systems might emerge from. So I'm just going to show you a quick demo of Robot Web in action. So this is a demo that I'm just going to run here on the laptop. In fact, hopefully we're going to be releasing this demo code openly soon. So this was built by Riku Murai from my lab. So let's just try this setting. So what I'm, we've seen many multi-robot SLAM approaches and something, but they might normally just have 5 robots. I'm interested in real scalability here. So let's run with 100 robots, which is no problem at all for these type of methods. I'll just change a couple of settings here to make it nice. So we've got 100 robots driving around. I should say there are a few kind of known beacons in this scene. So these black points here, these kind of just to set the coordinate frame here are known beacons. So if I start running this, so you can see all these robots driving around. If I just change the visualization a bit, so we've got 100 robots running around, and they're basically making relative range bearing measurements of each other when they get close. So this is the measurement pattern. So you'll see that the robots have short range sensors. They make measurements either of these fixed beacons or of each other when they get close. And you can also see that each robot has, when it moves further away from any of the other robots, you can see there's a sort of divergence, there's a ground truth and an estimated position for each robot. And you'll see them sort of split apart. But when the robots go back close to the other robots or close to the beacons, get good information again, they can really lock back on. So I'll show you if I temporarily just turn off their inter-robot measurements. So I've just set their sensors to have 0 range, so they're not making any measurements, and you see that we quickly get this big divergence. If I turn this back on, they start measuring each other again, and most of the robots will quite quickly lock back onto good position. So, tell me another factor graph solver that could work in this kind of incredibly dynamic sort of situation and run, fast and efficiently like this. Okay, so let's just go back. So I want to show you briefly something we've done very recently, not quite published, that builds on to that Robot Web work to talk about auto calibration. So any real robot system, as I'm sure anyone knows who's done real robotics, calibration is a real problem. So what about in this multi-robot localization problem? So what we're assuming in the demo I showed you so far is that every time we make a measurement, it's like one robot is using a sensor to make a measurement directly of the relative pose of another one. But realistically, what's really going to happen is that each robot will have a sensor, which will be something like a camera, and then it's making an observation of some observable point, which we'll call the marker on another robot. And those two things, the sensor and the marker, will each have some unknown or possibly it might get knocked or something, position relative to the robot. So it will have some unknown kind of extrinsic calibration. Now, we probably, a lot of people who've worked with factor graphs will know it's possible to do auto calibration within things like SLAM. And the way that you do it is you add extra variables into your system that represent things like the unknown extrinsics of sensors. And then those just become part of your solution. So in this work, we've just shown that we can still do exactly the same thing in this multi-robot setting where we're using Gaussian blue propagation to do the inference. So we've kind of got a demo of this with many simulated drones flying around. So this is in full 3D. Each drone has a camera and it has a marker. And so the camera of one drone will observe the marker of another drone. And then each of those cameras and markers have some pretty reasonable uncertainty in their extrinsics. So they might be uncertain to within several centimeters and several degrees. So if you don't account for that, the system will not work at all. But here we're going to simultaneously solve for the motions of all the devices and auto calibrate those extrinsics. I'll just skip forward here. So here we show that kind of happening over time. where we start with this kind of really random distribution of extrinsics over all the different robots, and we end up kind of auto-calibrating to something quite accurate. So, you know, what I'd like to say about that is this idea of kind of that you can add in extra variables that represent unknown things into this framework. This to me is the starting point of something much more general, and I think a path towards integrating methods like this properly with learning, because I think these extra variables could gradually become, you know, representing much more sort of generally unknown things. Like you could have a set of variables that represent a sort of MLP-like structure of the calibration of some weird sensor that is not just something you don't know, which is one number, but is something much more general that you would try to estimate. Anyway, that's a bit of a hypothesis and ongoing work at the moment. So I've just got a minute left, but I'll show you one last thing, which is I mentioned, you know, you can use factor graph solvers, not just for estimation problems like SLAM, but you can use them for planning. So we've done some work on using Gaussian bleed propagation in multi-robot planning. And again, the best way to show this is via a demo, which is thanks to my student Alok Patwardhan. So this is a simulation of, you know, you can think of it as vehicles crossing a junction. So we've got fast moving vehicles. Some of them are turning right, some of them are turning left. And you'll see that what they're doing is dynamically altering their paths so that they will avoid each other at the junction. So this is all you know, running in real time, and I can just kind of show you how it works here. So essentially, each of these robots is planning its forward motion over a series of future time steps. So it's deciding where it will be, you know, at a number of fixed time steps over the next sort of forward 2-second window. And so basically, there's a factor graph that says, you know, my forward time steps, first of all, they're connected by factors that say something about my smoothness and dynamics. So I can't jump around randomly. I know I've got to follow a path that has some smoothness, but also I don't want to collide into any other robots. So forward time step nodes of robots at the equivalent time have factors between them that basically say, you know, we shouldn't crash into each other. So what the important thing is that the factor graph structure in the end of this is pretty much exactly the same as the robot web multi-robot estimation problem. But instead of these being kind of poses back into the past that I'm using for estimation, they're poses into the future that I'm used for planning. But computationally, it's very much the same. So we can do very much the same thing. We can solve this in a distributed way with this kind of web pages and message passing. And again, very, very scalable, and it just works surprisingly well. Okay, I'd better finish there just to conclude. You know, I think this work on distributed estimation is quite important if we're really thinking of a long-term future in robotics, and especially things like interoperability and efficiency in robot systems. And to mention my affiliation, so I'm leading the Dyson Robotics Lab at Imperial College, where we do academic work on 3D, on reconstruction, also manipulation, thinking about applications in home robotics. And I'm also co-founder at SlamCore, which is a London-based startup doing applied spatial AI. Thank you.
Thank you for Professor Andrew Davison. So before we move on, does anyone have any questions for the Professor Andrew Davison? Thank you for the very interesting talk. I just have a question. So Web4, do you think it's compatible with robot operating system, and if so, are you planning to release a package in the future?
It's not something I've thought about yet, but I don't see why not. I'd be interested to talk about that. Yeah. Thank you.
So the Gaussian propagation, how would you get and then distribute it?
So I mean, it's different in various ways. So it's basically locally second order rather than first order. So every message that you send is sending, you know, a variable but also with the kind of local properties of Gaussian distribution. So you can think of it as having a sort of local learning rate at every single variable. And so you don't have to set anything like, you know, a global learning rate. I mean, I'd be interested to discuss that more in detail, but.
I would ask the comments on risk markets on like population models, large language model, static model, and large language model like reading how several ranges from these population models.
I mean, clearly that's a bit out of the range of this workshop, probably. I mean, of course, those things are amazing. I guess my current thinking about robotics is, amazing as they are, I'm not sure how much they're going to help with the real problems of robotics at the moment that are quite low level. So I see them as an amazing kind of interface to robotics and giving us answers to some of those high level, you know, questions of, you know, how do you talk to a robot? How do you interface it? How do you give it a high level plan? But when it comes down to the nitty gritty of how am I efficiently going to estimate my position or pick up a cup or something, I think we need something a bit different still, and that's probably what I'm more focused on than working on. So, thanks.
Okay, thanks for the professor and Alison. So, for next, we have one great honor.
Hi, sorry, we can't hear it.
Can you hear me now?
Yes, we can. Thank you.
Okay. I think so. I switched on my microphone, I guess. All right. It's from monocular SLAM to 3D dynamic scene understanding. Maybe to give you a bit of background of where I'm coming from here. We've worked for almost 2 decades now on the topic that we started in 2005, working with the company Daimler. We put cameras into cars. We started filming the action in front of the scene, in front of the car, and then we started trying to reconstruct the 3D structure and 3D motion here, color-coded in red, in order to distinguish obstacles, to predict their motion, to anticipate what's going to happen next. And then at the time to send out warning signals to the driver or possibly engage and actively brake to avoid the accident. But as you know, self-driving cars is a hot topic, but it's slow in the making, slow in the coming, and people are waiting and waiting for the self-driving cars. What I see, though, is that in recent years, the topic has been picking up momentum again. We see a lot of legislation being put in place to support self-driving, a lot of technologies, different levels of autonomy hitting the markets. But the biggest challenge, in my view, that prevents these technologies from scaling across the globe, they take technologies without sacrificing humans.
And this is something I'll come back to towards the end of my talk. In this talk, I want to focus on two aspects. One is on how to develop, in particular, SLAM-like techniques to capture the 3D world. And secondly, how to capture the dynamics of the 3D world, how to capture how humans actually drive. Something that I think is very important for self-driving cars to engage with human drivers. Well, SLAM has a long history. We've already heard some of the pioneers here, people like Mark, people like Andrew Davison, many others. You know, this is one of the even older pioneers. He's older than you, I think. This is very old. 1930, before the advent of computers, and he showed this classical result that if you observe corresponding points in pairs of images, you can recover camera motion and 3D structure. And this kind of paved the way for later 3D computer vision for all the techniques that ultimately led to things like bundle adjustment, etc. I don't really talk about bundle adjustment, but maybe two short advertisements, if I may. We've been doing a lot of work in this area of developing novel numerics for accelerating bundle adjustment, for making it more scalable, also for making it significantly more memory efficient. This is work by Nico Demo and collaborators called square root bundle adjustment. And sorry, it's a bit small on the screen, but there are significant improvements in accuracy, speed, in particular, up to 42% faster than existing alternatives. This is a follow-up work with Simon Weber and collaborators, an entirely new way to numerically solve bundles and features. We call it power bundle adjustment, and here's where the benefit is it's faster and it's also significantly more memory efficient. 5 times more efficient. What I want to focus on in this talk, though, is real-time visual SLAM, or structure from motion, as it was originally called in the vision community. Some of the first real-time capable methods emerged around 2000, and some of the pioneers behind these works are here in the audience, people like Andy Davis. A lot of these works actually follow very closely in Krupa's footsteps. They extract points, they estimate correspondence between points, and then they reason on camera motion and 3D structure. So this is what I would call the classical pipeline of multi-view or 3D reconstruction. One of the shortcomings is that you typically make mistakes in the extraction of points in the identification of correspondence, and most methods have a hard time recovering from these errors. There is, approaches to ransack, etc., to re-estimate correspondence, but some of this is rather over the last years. Starting with techniques like LSD SLAM, is that we go straight from the raw sensory data, the brightness values of your camera, to a reconstruction of camera motion 3D structure. In the end, we also reconstruct points, but the key difference is that the loss function that drives everything is brightness consistency. It's not the reprojection error of points, but it's an error that is directly defined on the sensory data, on the brightnesses. This was LSD SLAM, to my knowledge, the first real-time capable large-scale SLAM method that could reconstruct not just a desktop environment. This was done, for example, in PTAM, really nice work by Georg Klein and David Murray. But here you can see we can really take this outdoor and reconstruct with just one single camera, fairly large environments with almost no distortion. And this is all real time. The code is online if you want to explore it. But I think most of you know this. It's been explored a lot. People seem to like it. The next generation to LS 2018, so it's a bit old already. The key difference was that we here jointly estimate 3D structure and camera motion in a single Gauss-Newton iteration. To make it real time, we have a window of optimization of the last keyframes. And that makes it scalable. And as you can see, we can go with just one single gray value camera through a subway station, back around, loop around, and come back to where we started from. And there's practically no drift. Practically no drift here means you see the bicycle is reconstructed twice. It's about 2 or 3 meters of drift on a distance of hundreds of meters and thousands of frames. So how can we evaluate this? How can we evaluate it? And I'm a big fan of real world evaluations because we've seen a lot of techniques that work amazingly well in simulated worlds, but often fail miserably once you take them to the real world. So what we did is we recorded a lot of real world sequences like the one you saw, and then we plotted the error in translation, rotation, and scale compared to what is still to date one of the most popular SLAM methods, namely warp SLAM. And you can read these plots in many ways, but if you say, what is the error on the best 300 sequences, then whereas warp SLAM has an error of 6, we have an error of 1. So that's a reduction by almost an order of magnitude in terms of error. I believe quite a significant reduction, not like 2 or 3%, almost an order of magnitude. Similarly, if you want robustness, you want this to work on as many sequences as possible. If you say the error should be bounded by 2, as you can see, we can warp SLAM can track 100 out of 500 sequences, whereas we can track 400 out of 500. So also a significant boost in robustness. We carried, and so one of the endeavors in our research over the last years has been to kind of keep pushing the limits of precision and robustness. And there's many ways to do that, starting from DSO, for example. You can infuse it with inertial information. This is work from last year's ICA. Lucas Stumberg, he calls it DMVIO. And here you see it's one single camera with an IMU, so much like what you have on a smartphone, right? We go up a flight of stairs, and then you see on the bottom left, we go into a tube that takes us 3 floors down. It's pretty dark in the tube, practically no visibility. Still, the system, using vision and inertia, is able to very robustly and precisely track this visual inertia system. And then we can go back up 2 flights of stairs to the second floor where we started from, go back into the room where we came from, and you can see the drift is very small. And this is just using a standard camera, and I believe unprecedented in terms of precision for visual inertia. So we thought, how about we create a startup to actually deploy these technologies in the real world. This was the beginning of this, one of my first startups. This is in different places. And the company was acquired in 2021. But what we developed in the Artisans and are still developing is sensory-based systems involving cameras, IMUs, RTK, GPS, etc., properly timestamped, etc. And then the spatial AI were the process of this data to generate large-scale maps, etc. Here is a whole fleet of cars, and we have 8,000 kilometers. And we can, as you see, semantically label all of this, distinguishing drivables, area, size, cars, with buildings, on a very large scale with very low costs. Just and so we think with a lot of the things we do, we are trying to really establish the carry perception. You saw we can tap into deep networks to extract semantics. We can also tap into deep networks to build better. In retrospect, the name was very badly chosen because it's convergence theory. It's a monocular approach. It's often cited as stereo in the literature, but it uses one single camera and basically hallucinates the second camera using a deep network. So you can feed these depth predictions of this, what we call StackNet, into a SLAM pipeline. In fact, in the follow-up work, we showed not just depths, but also pose and uncertainty predictions. All of it can be fed into a SLAM pipeline, both in the front end, in factor graph formulation, and in the back end optimization. As a loss function, basically saying find a reconstruction such that the 3D world is compatible with what the deep network predicts for every key frame. And these predictions are metric in units. That means even from one single camera, you get metric reconstructions of the world, and essentially no scale that you typically have in monocular standards. But with this deep learning enhanced monocular system, you don't drift in scale. So you get very accurate, almost drift-free reconstructions from just one single camera. No IMU, no GPS, no stereo, just a single camera. There's also quantitative numbers, I skipped that, but it's definitely very, very accurate. We looked into, can we use deep networks to actually generate dense worlds? This is one most photorealistic, very dense reconstruction of the world. Now, if you think about it, sure, the point cloud you see here may not have the same precision as LiDAR-based point cloud, but I would argue it's sufficiently accurate for driving. And so the question really is, do we still need a LiDAR to sense 3D if just with a single camera I can get these kinds of dense reconstruction? And I get the colors. I mean, you have the camera anyway, because you need to read the stop signs, etc. Right? So once you have a camera, you can use these techniques to generate kind of digital twins of the world that you can also then use for testing, you know, cars in a reconstructed 3D world that matches the real one. Felix went a bit further, and this is kind of density-based approach. It's a little bit inspired by NERF, but it actually learns from data, and what it learns is to predict from just one single image a full 3D reconstruction of the scene. So you see it here, what we architecture that basically for every pixel in the given image predicts the density as learning approach. And so you don't need ground truth, and you can train. Basically what allows you is it allows you to reconstruct even the unseen areas here. Pixel NERF doesn't do that. Or monodepth 2 also doesn't do it here. You see monodepth 2, it can only predict the first depth value, not where only where the car starts, not where it ends. Right? With training data, we can use system to also learn the extent of the objects in the world and thereby generate more plausible, full-blown 3D reconstruction. There's more videos on the net if you're interested. I come to the second part of my talk, and this is capturing the dynamics. With SLAM, we've been predominantly focused on the static world, reconstructing the 3D structure of the world, its environment. But as you know, once you deploy self-driving cars in the human world, there's a lot of other participants. There are cars, cyclists, pedestrians. And I think one aspect that has been hugely overlooked by a lot of self-driving car companies is we need to understand how the humans behave in traffic. Once we deploy a self-driving car along with human drivers, it has to be able to anticipate how do humans act. What is this bicycle going to do next? What is that pedestrian going to do next? What is this car going to do next? And we as humans do that all the time. We negotiate with other drivers, right? I drive here, I see another car coming. I have to constantly anticipate what are others doing in traffic. But do we know how humans drive? Do we have a complete model-based understanding of the spectrum of human driving? No. Do we have all the critical scenarios that can potentially happen? No. Why? Because in self-driving cars, you put the camera in the car, and even if you drive millions of miles, typically you never see an accident unless you're involved in one yourself, because you only see the things right in front of you with the sensor on the car. right? If the car in front of you brakes, you have no clue why it brakes because you don't see what that car sees, etc. So you cannot build a complete model of how humans behave in traffic. And so you need to get this data of how humans drive, and you need to be able to interface, for example, in simulated worlds. We have beautiful simulation engines like Carla, right? But the agents in these simulations, do they behave like a real human? Typically not, right? But you need the real human aspect in these simulations. So how can we get at it? So obviously there's vehicle data. It's simple. You know, we've been doing it for 20 years, putting cameras in cars and just filming, right? But you have a limited view, right? Then there's surveillance cameras that have a kind of a better view of kind of a larger area of traffic. Also easy because it's 24/7 data collection, but fixed camera. And then we have aerial imagery where we can actually take drones and fly over critical areas like intersections, etc., and record. And this is what the company Deep Scenario has been doing. It's another startup that I've helped create. They just raised this year, the first seed funding, and they're now building a tech stack, and this is what it looks like. They first reconstruct the 3D environment from static from images, classical computer vision, 3D computer vision, and then we detect the cars in the dynamic objects, cars, cyclists, pedestrians, everything in this environment. And then we can take all of this data, and these are 3D detections, not 2D, but 3D bounding boxes. And then we can, you know, for all the objects, we can map them into a simulated environment. Here's some examples of what they've achieved. So there's 3D data extraction, and you can see it works on a very large scale. We can track hundreds and hundreds of cars. And note in the center here, there's a small car that's trying to merge into flowing traffic. And it's not easy, but you see, we get all this data, or here other examples, see in the center, the car, what it's doing. It's pretty crazy, the kinds of things you see when you film critical areas from the air. Here as well, you know, if you look in the middle, there are pedestrians, there are persons moving, there's bicycles moving, the cars are trying to turn, right? And you see this big truck, the yellow one, it's kind of more aggressive. It just turns in between the pedestrians and cyclists. The car here lets the cyclists go by. You know, it really shows you in great detail human behavior, you know, how do cyclists behave, how do cars behave. Here's more examples of chaos at an entrance to a highway, right, where we can really extract information about not just the average human driver, but the whole spectrum of human driving, and including accidents. See here, for example, on the bottom, there's pedestrians crossing. The car moves, then it stops, and the other car, in the aim of trying to clear the intersection, just crashes. And so we regularly have these critical scenarios of, you know, accidents, etc., that really capture the full spectrum of human driving. Or here, a very interactive turn where a straight going car goes right in between the turning trucks. Right? And so you see, we can track the whole traffic at very high precision in 3D. And so this is what Deep Scenario offers, not just the tracking, but then in collaboration with DSpace, we're now in the process of feeding simulations with the data that we extracted. Really real-world physics-based sensor simulations like this one, where every agent that you see here is an actual human driver, right? And you can simulate the visual systems, you can simulate LiDAR, you can simulate all sorts of different sensors at different day conditions, etc., just from the data that we check. There's a lot of customers that we've been working with, active Audi, Bosch, BMW, Mercedes, Volkswagen, Hexagon, Sensat, Torque, and many others that we're working with. And if you're interested in collaborations, just please reach out to Deep Scenario. So I think we're getting to the end of my talk and to the lunch break. I talked about SLAM, about capturing the 3D world with direct SLAM methods, with deep learning enhanced SLAM methods like DVSO and D3VO. I talked about semantic mapping using SLAM and deep learning. I talked about how to deploy deep learning to generate photorealistic kind of digital twins of the world from just a single camera. And also fully dense 3D worlds from just a single image. And lastly, I talked about the efforts of the startup Deep Scenario in capturing human driving and human pedestrians and cyclists in real-world traffic to feed simulations and generate real-world models of how humans actually drive. Thank you.
Thanks for the great talk from Professor Daniel Williams. So does anyone has a question for great talk?
Question related to us, first great talk. Very good question related to the monocular kind of scale reconstruction within. For cars, I see this working trivially because of the high level ground, that's fixed and so on. Have you validated that scenario also for, well, let's say, a head-worn camera or like handheld scenarios?
So that's a very good question. As I said, you can recover metric reconstructions and the scale from a single camera. You know, in textbooks, you always read that it's not possible. Once you train a neural network, you can do it. But obviously, there is the aspect that it depends on the training data. You have to assume that somehow the world that you're recovering is in some sense related to the training data. So we found for self-driving cars it works. We found it generalizes. You can train it on Kitty and apply it to cityscapes. So different city, different sensory systems still deploys, still works. But there is some degradation when you take it from Kitty to cityscapes. The performance goes down a little bit. And when you take it into a completely different environment, say head-mounted, we've tried it, the performance also goes down a little bit, but surprisingly, it still works. Why that is, I don't know. So there is something that these networks extract from self-driving scenarios that seems to still apply to other environments. But obviously, you can expect the more different your environment is from the training environment, the more it's going to break down. The nice thing, though, is it's all self-supervised learning. So you can just easily retrain in your environment.
Okay, does anyone has other questions? Okay, thanks for the great talk for the. Thank you. And I would like to express thank you for all the professors today.
Are any of the organizers able to hear me?
Yes. Hello. Hello, E. Can you hear us?
I can
Maybe
hear
I
you.
can. Oh, okay. Yeah, we'll check.
Just wondering it's already past the start time. What's happening?
Oh, yes. Sorry, I will check it with the organizers on site. Yeah. Okay. I think I will contact them. Hello, E. And Shibo, I think I cannot hear you. Maybe the microphone is not open.
Yeah. Can you hear me now?
Oh, yeah. Yeah.
Okay, yeah. Hello, everyone. So it's a great honor and to have Professor Tim Bufford and to provide a talk, learning perception components for long-term path following. And Professor Tim Bufford, he's from the University of Toronto Robotics Institute and work in the area of autonomy for mobile robots, targeting for a variety of applications. Professor Tim Bufford is an ICCV fellow and has received 2 papers awards at the ICCV International Conference. And he sits in the editor boards for the IGR and the field robotics and the foundation board for the robotics. So let's welcome to the Professor Tim Bufford to have an excellent talk for us. So Professor Tim Bufford, I think that you can go ahead.
Okay, thanks so much. Let me try to share my slides.
Okay.
I think you have to stop sharing your slides first.
I will stop sharing. Okay.
Can you see my slides?
Yeah, we can see your slide.
Okay, great. Well, thanks so much to the organizers for the invitation, and I'm sorry I couldn't be with you there in Paris. Unfortunately, I'm here in Detroit attending the IROS conference this week. It's unfortunate that it was at the same time. So today I did want to talk about a collection of projects related to learning different perception components for long-term path following. So let's jump right in since we don't have so much time. So what is path following? From my perspective, path following has to do with having a mobile robot first be driven through an environment where it builds a map, and then the idea is that it should try to drive through that path again autonomously. So this is just a video from several years ago where we have a robot navigating completely using vision. It's driving a path that it was previously taught, and now you can see that it's driving exactly in its tracks. And there's a lot of different applications that this can enable. The hope is that we can do this in any kind of environment, particularly unstructured environments where we don't have a lot of easy man-made infrastructure to rely on. As I said, we drive the path and then we try to repeat it. We'd like the implementation to be pretty efficient, so not relying on a lot of compute or a huge number of sensors. And we'd like it to only sort of have one training example of the path before it's able to start repeating. We might not want to rely on GPS. Here, we're not relying on it. We're also not relying on IMU. In this basic version from many years ago, we didn't even have DNNs, or we didn't even have a global map and no semantics or structure. And then the nice thing is that we can actually teach lots of these different paths, kind of like over here on the left, and interconnect them. And then we can compose those paths into different routes that weren't exactly the combinations at training time. So it's composable. And then this is kind of also just a nice framework for doing lifelong learning. And so some of the projects I'll talk about today we'll exploit the fact that we can drive these paths many times and build up data sets and then try to learn improved components, perception components in particular, that will help to deal with some difficult issues. So anyone who's done path following problems or any mobile robot navigation outside kind of realize that vision gets pretty difficult pretty quickly when the scene can change significantly from when you build the map until when you're repeating these paths. And so this slide just indicates some of the main issues that we've tried to deal with over the years. Lighting is sort of the one that comes to the fore right away. You know, you might teach in daytime and then want to be repeating at night. So here's an example of us driving at night with headlights on. Of course, LiDAR and radar are less affected by this, but cameras have some advantages still due to their passive nature, low power, and low costs. So there's still some advantage to trying to deal with cameras. A little bit further into the time frame, weather starts to become an issue. So and seasonal change. So here's an example of a robot driving in the winter, and you might like to teach the path, say, in the summer, and then still be repeating that route in the winter. So that's another challenge that we can start to deal with. And then finally, there's, of course, the obvious thing of just obstructions on the path. So you can't really guarantee that just because you taught the robot a path that was obstruction free, that when it goes to repeat, it's got no obstructions. So you might like to be able to avoid obstacles while following paths. So in this talk, this is sort of my outline of the talk. I'm just going to talk about a collection of different projects over the last 2 or 3 years where we've been learning specific components within that overall pipeline that I just demonstrated in the first video. Everything from learning LiDAR and radar features for odometry, learning camera features for localization so we can match daytime to nighttime, learning a radar distraction mask so we can know what to pay attention to in noisy radar data, and then learning a change detector that will help us detect where obstacles are so that we can avoid them on paths. So let's jump into the first one, which is learning LiDAR and radar features for odometry. So a theme in this talk is basically that I'm not trying to learn everything end to end. Of course, that's one end of a spectrum. The other end is that we don't learn anything. We just handcraft all of our algorithms like we did about 10 years ago. And I guess in this talk, we're trying to sit somewhere in the middle where perhaps we're learning these front-end features, but then still combining those with quote unquote classic state estimation tools in the back end for doing things like odometry and localization. So that's kind of what we're trying to do with all of these projects today. So let's talk about this first one, learning LiDAR and radar features for odometry. And so this actually builds on an earlier paper that we put out a couple of years ago that's indicated in the bottom right here called Exactly Sparse Gaussian Inference with application to derivative-free batch nonlinear state estimation. And it's basically a technique for being able to simultaneously do state estimation, but also do parameter learning. And so we've exploited this to try to learn features for LiDAR and radar odometry. And it actually builds on the idea of expectation maximization. And so the way it works is in the E step, we take some, say, LiDAR scans in a mini batch. We do a forward pass through a network that's able to extract, in a differentiable way, of course, a number of interesting key points, covariances, and descriptors for those key points. We then match these features across time, and we build them into a differentiable factor that we put into a larger factor graph state estimation problem. We can then actually also add in other sensors that have nothing to do with the learning problem. So maybe we have some wheel odometry or some IMU data that we want to put in. And the interesting point with this framework is that our state estimator does not have to be differentiable. So in the forward pass, we're just sort of going in the forward direction and doing inference, our network's outputting features, and then we're trying to estimate our motion. But this part doesn't have to be differentiable. In the M step, we hold the distribution over the trajectory as fixed, and then we just use standard deep learning tools and we back propagate back through the network to try to improve the features that we've been learning. And we just go back and forth between the E step and the M step until we get convergence. And as a video, we can look at this thing over here on the left. This is actually training. So what you're seeing are the iterations of training. And you can see at the beginning, we have randomly initialized weights and the features that we're trying to use are really poor. But as we try to improve the trajectory, and then improve the features and keep going back and forth between those, we're actually able to eventually unfold this and estimate a pretty good trajectory with fairly useful features. And I should mention we're doing this completely unsupervised, so there's no ground truth of any kind. And then here's a video at test time where you can see the features. We're estimating the trajectory. It's nice and smooth. And because we did this in this non-differentiable way for the trajectory part, we have a very fancy state estimator that's doing continuous time state estimation. It's got smoothing factors, all kinds of stuff that would be hard to make differentiable. But this tool is able to let us do that. And it's not the best LiDAR odometry in the world, but it's comparable, I guess, to some of the state-of-the-art tools. And I thought that was kind of neat that we can do that completely unsupervised and learn features. So switching gears, I'm moving on to the second project in my outline now, where now we're talking about learning camera features for long-term localization. So perhaps we want to build a map in one condition and then drive the route in another condition, and we want to be able to match these things directly. So this time we put these into a pipeline where we again use a network to output features, scores, and descriptors. We match those in a differentiable way. We then put them back through the inverse stereo camera model to produce Euclidean features, which we then align using a differentiable, this time pose estimator. So this is a differentiable implementation of SVD, and that outputs the pose. So this time we're going to do this problem semi-supervised. And by that, what I mean is we have some ground truth on the pose, but not on the features themselves. So the idea is we're only really learning this part, and the rest of this pipeline is known and differentiable. And we get ground truth labels through another algorithm. You can ask me that in a question later if you want, but an older algorithm that's able to produce pose in a completely unlearned way, but it's kind of expensive. So we get these labels, and then we just back propagate through the whole pipeline, and we only really keep this part. So this is really just a test fixture that lets us do the learning problem. We can then take these features and put them into a fancier state estimator that we run online, where we can do filtering and things like that. So we don't need to use this very simple pose estimator when we're actually running this on the robot. And so to train these features, you need a lot of data. So we gathered some data, or took a data set that we gathered way back in 2016 that had a lot of lighting and weather variation. And we were able to train these features and then deploy them in our larger software framework on the real robot a couple of years ago. And so we drove a much larger path in the area in which we gathered the data for feature training. And here's sort of a qualitative view of how well those features are doing. This video on the left is the main story. So these little red dots are features that are matching back to a map that was built at around noon on a sunny day. And you can see where, as the video is switching, these are different conditions under which we're then testing the features and matching them back to that sunny day. So right now, this is nighttime, and we're matching these features back to daytime directly. And it's good enough that this robot's actually driving autonomously. So this is not just data set testing, but the output of closed loop localization running on a robot. And a little more quantitatively, we can see here that we taught the path at noon and we tested at a lot of different times. You can see as a proxy of how well the localization is doing, you can see the number of features that are being matched at these different times of day as we move further from the time at which the map was built. And we still have lots of features. This is sort of at the nighttime, like before the sun comes up. You can see there are less features, but there's still enough that the robot can drive in closed loop. And we actually did that 100% successfully across this lighting experiment with only 4 centimeters deviation with respect to the path. We did this experiment even over a longer period of time, over multiple months. And eventually the features that we learned weren't able to match all the way back to the very beginning, but it's a huge improvement over what we were able to do before we were learning these things. So they sort of last for months now instead of hours. And then you might ask, well, do you need to do that semi-supervised? In fact, no, we can take the expectation maximization framework that I talked about for the LiDAR features earlier, and we can try that out on the camera features as well. And so in this case, we were able to do completely unsupervised learning of these camera features. And due to a couple of other changes in our architecture, particularly that we switched to using a pre-trained network, our unsupervised features even beat the semi-supervised features that I just told you about. And you can see over a number of different lighting conditions that we were able to get. This sort of color here is the best that we're doing. And that's completely unsupervised feature learning. So that was presented at ICRA earlier this year. And then even one step further, we had a paper that was just presented here at IROS yesterday, where we were not only just learning features, we were, in addition, learning an image style transfer network that was able to take the appearance of the map scene or the live scene, doesn't matter which one. I think it was the map scene in this case. So you can see a nighttime map, and we were trying to transform that into a condition that looked like the live images. So we're trying to make it look like daytime images. And so using this combination of style transfer and feature learning together in a single pipeline, we were able to back propagate through this whole thing and learn even better features or a better feature matching technique, I guess, than we were able to do with just the features alone. And I think this picture is quite interesting. So on the left, we have the output of our network just before the softmax layer where we output the features. You can kind of see what it's firing on. Blue is it's more interested in things that are blue and less interested in things that are green. And you can see if you're just using feature learning, you're sort of still firing on a lot of this low-level texture. But once we do the style transfer and the feature learning together, I think it's quite interesting that now our feature detector is firing more on key interesting landmarks in the scene. And you can see it's picking out the poles in a fence or these pylons that are sitting here. So that's actually quite a qualitative difference in what we're able to learn by adding in the style transfer network. And the bottom line is that our localization is quite excellent now with this combination of these two things. We're getting down to just a couple of centimeters of error compared to ground truth from our imagery. So localizing with respect to the path that we want to drive it, we know where we are within a couple of centimeters now. So that's a huge improvement over what we were able to do a couple of years ago. Switching gears again to the third project on my outline, I'm going to talk now about using radar for localization. So perhaps we've driven a route and we built now a car in a city, and we built a route map of that route using LiDAR, and we want to localize against it using radar. And you can kind of see in this video what the output of our imaging radar sensor looks like. It's a 360-degree sweep. But you can see there's a lot of artifacts. There's a lot of strange effects that come along with radar that make it a bit difficult to work with. So what we wanted to do in this project is learn a distractor mask. Basically, we'd like to learn what to ignore and see if we could learn to ignore the things that aren't real effects in these scans. And so again, we built a network that can do this. So we take the raw radar scan, we try to put it through a network that learns a weight mask. So it's trying to learn like a weight that classifies every pixel in this scanning image as to whether it's a good thing to pay attention to or not. We then extract our actual features, and then we apply the weights to every pixel so that we get this weighted point cloud coming out of our radar scan. And then we match that to the LiDAR map that we built previously using a differentiable version of the iterative closest point algorithm. And then the idea is that we can just back propagate through this whole thing to learn this distractor mask network. And it turns out that we can do that. So our network tends to learn to pay attention to things that are closer to the vehicle. Oh, by the way, we tested that on this data set called Boreas that we put out last year. So that's free for everyone to use. There's nice benchmarking tools for doing radar and LiDAR odometry. So we use some data from that for testing. And you can see that here are some examples on these two rows of distractor masks that our network has learned. So these are the raw radar scans, and then this is sort of like more like what we're actually using for localization. And the result of learning this distractor mask is that we can cut our errors basically approximately in half. So this is before we add the distractor mask, and this is after. And you can see we're down to sort of 12, 15 centimeters error. And that's just on one radar scan. So if we put these in combination into like a fancier state estimator online, rather than just one scan, so that we're doing filtering and smoothing, we can actually do quite a bit better than that. But that's just the results on a single scan. So that's working reasonably well. And then the last project I wanted to talk about is the idea of now heading towards the idea of obstacle avoidance while path following. And anyone that's done testing off-road and trying to detect obstacles, it's pretty difficult. When you're in a more urban environment with a flat ground, segmenting out obstacles is not so difficult. But once you start to head into tall grasses and trees and things like that, detecting obstacles is actually pretty hard. So we don't try to detect obstacles. What we try to do is change detection. So because we've driven the route and we built up maps previously, all we try to do is try to figure out what's different in the live scans from the map. And in this case, we're going to be using a LiDAR to do this change detection. So here's just a cartoon. We want the robot, it's supposed to follow this purple path, but there's somebody standing on it. And so we want to deviate around that. So we need to detect this change. This person will look like a change compared to the map that we built when we taught the route. So to do that, we actually use range images from our LiDAR. We compare the range images to each other. We then put the differences into a neural network that's hopefully going to try to find these changes. We use a number of different losses to encourage the network to find changes, to not find too many changes, and to make those changes consistent over time. And so our loss is built from those three things, and it's done completely unsupervised. So there's no ground truth labels that we use in the learning. And by gathering a bunch of data just from the robot, without any ground truth, we're able to learn a network that can do this change detection. And this video is kind of showing what that looks like. This is what the point cloud from the LiDAR looks like. And then this is what the change detection is looking like. And you can see this little green person here. So to evaluate this, what we did was we covered one of our grad students with this retroreflective suit, which is very easy to segment out from the scene so that we can have some ground truth labels. And then that was showing earlier like that we could detect those changes pretty reliably. And so again, now we're putting that in closed loop on this robot. It's driving around a path, and you can see that it's able to detect the changes and then make small deviations to its long-term route to avoid those obstacles while still following the long-range path. That's sort of a work in progress. You can see we're testing still on fairly easy scenarios, but we did do some testing, as you saw in the previous video, where we're in tall grass and amongst trees and things like that. Oh yeah, this part of the video. And it's working better than sort of the naive baseline of just comparing the closeness, the nearest neighbor closeness of points to the map. That produces a lot of artifacts that we don't really want to, a lot of false positives in particular. So this network is much better at not getting false positives than the naive baseline. So that's my talk for today. I just wanted to keep it fairly short. I know you've got a short timeline. Just thanks to all the students and collaborators that have done the work and the sponsors. And I'll just leave you with a few summary thoughts and questions on this slide. So I would say after a few years of working on these things, learning is definitely letting us do things that we couldn't do before, particularly matching daytime to nighttime. Wouldn't have dreamed that that was possible 5 years ago. Unsupervised and semi-supervised learning, I think, still benefit quite a lot from using classic state estimation tools in supporting roles, either through labeling data sets or providing context for learning. And so, related to the context is that although we may not want to learn the entire pipeline end to end, we might want to train it end to end so that we can learn, say, features that are useful for the actual tasks that we're interested in, like localization. So being able to backpropagate through a state estimator is very useful. And then just to make the counterpoint, we don't always have to actually make the state estimator differentiable. I think we could either learn something using a simpler state estimator that is differentiable and then deploy, say, the features in a more sophisticated estimator, as we did in a few examples in this talk. Or we could use this other framework that I mentioned that uses expectation maximization and a state estimator that's not differentiable to learn features. And then I would just leave you guys with one final thought, which is that I think it's tempting to just sort of crank data sets these days. There's a lot of them out there, but I really think there's value still in deploying what you've learned on real robots and trying to validate that what you've learned is actually useful for the original task. So all of the talks, all the things I showed you today, we've deployed on real robots to really make sure that the things we were learning are actually useful. So I think I'll leave it there and happy to take any questions if there's time.
Thanks, Professor. Thanks for sharing these insightful.
Sorry, I can't really hear you.
Does anyone have problems with questions? Oh, actually, you have a question.
Yeah, I don't really hear what you're saying. You might have to move closer to your microphone.
So can you hear me, Professor Tim Buffer?
Yeah, much better. Yep.
Okay, cool. So does anyone has questions? Okay.
Hi, Tim. Can I ask, adding the LiDAR safety layer, how do you think about that, given that with visual teach and repeat, it's typically assumed that the safety comes from following the same route?
I think that's Morris. I can't quite see. But it sounds like you. I don't quite understand the question. Which LiDAR safety layer are you speaking about?
So previously with visual teach and repeat, you're precisely trying to follow the same trajectory, which kind of defines the safety case for the system. With this deviation based off of LiDAR, how do you think about the safety case in that situation?
Yeah, that's a good question. We've been thinking about that a little bit. I guess our answer right now is that when we teach the path, we're exploiting some human knowledge there to define the path. Our hope and what we do in our interface right now is we have the human also define a corridor around the path for which the human at teach time believes that the path is safe. So you could imagine like a 2-meter corridor either side of the path. And the human is saying, I think if you stay in this 2-meter either side of the path corridor, you're going to be fine. So then if that's true, which may or may not be true, but let's say that that's true, then all we have to do is detect changes and try to avoid them. So as long as we stay within that corridor. So our path planner is actually BitStar. I don't know if you know that algorithm, but we're using BitStar to avoid these obstacles. But BitStar then gets this corridor constraint so that it has to stay within the 2-meter corridor that was given to the algorithm. That's the answer we have so far. So the human is again sort of deciding where the safe corridor is up front.
Okay, thanks very much.
Okay, does anyone has other questions? Okay, thanks for the Professor Tim Buffer, and it's very great talk. So let's move to the next speaker. It's from Professor Shuba, and so can you set up?
Wait. I think Tim might need to stop sharing so I can start sharing.
I'm working on it. There we go.
Okay.
All right. Bye, everyone. Enjoy your workshop.
Okay. Wait a second. Okay. Hello, everyone. So it's my great honor to introduce the Professor Shuba, and he is an assistant professor at Carnegie Mellon University in the Robotics Institute. And he is a part of the computer vision group, and he's very interested in the building perception system and can infer the spectral and the physics architecture in the world we can observe. And for today, he will provide a talk about probabilistic pose prediction in our workshop. Welcome to the Professor Shuba. Yeah.
Yeah, thanks for the introduction. I hope I'm audible. If not, please feel free to tell me to speak louder or something. So yeah, it's a pleasure to be here. I'm sorry I couldn't be there in person, but hopefully sort of the remote, now that we're all familiar with sort of Zoom talks, hopefully this won't be too bad. So yeah, I think the workshop was titled on sort of SLAM and robot learning, but today I wanted to give you some updates on a slightly different research agenda that we've been following, kind of related to estimating cameras, but in a rather different setup compared to what you would see in sort of a normal SLAM setup. And so in that context, I want to talk about this line of work from our group on probabilistic pose prediction. For the last couple of years, I think in my group, we've been looking at this task of what I call the Craigslist problem, which is anyone who wants to sell any object they have on Craigslist will naturally upload a small number of images of that object. So for instance, there'll be these 4 images of a desktop monitor that, let's say, someone wants to sell. And given this, you want to be able to get sort of a high fidelity 3D reconstruction of this object. And of course, the goal is we want to be able to do this from a few casually captured images. So again, an average user will not painfully go around because they don't really know what sort of data makes a SLAM or SFM system work. They'll just take 3-4 images of an object that they want to sell. And it could just be a generic object, right? This is something, they may sell arbitrary toys, etc., etc. And so we want systems that can go from these small number of images to 3D reconstructions of the object. And really this problem, I think, kind of breaks down into 2 sub-problems. One is, given just a small number of images of such a generic object, we want to be able to register these images together, estimate pose of all these images from just a handful of views. And secondly, given our understanding of these views, if we have understood poses, we want to be able to then reconstruct the 3D structure of the underlying object. In today's talk, I'll sort of focus on the things on the left, but I want to sort of give you a brief highlight of some results from a group of the problem on the right, just to convince you that if we can get poses, we can sort of eventually use these to get 3D. So here's this sort of a result video of one of our recent projects. Feel free to go and look at the website that's sort of cited at the top. But given just a handful of images, sort of 2 images, or actually 3, 4, etc. images, we can get reasonable 3D reconstructions of generic objects. But all of this is assuming that we know the camera poses corresponding to these 2, 3, 4 input images that are available as input to the system. And so really, I would say we've made a lot of progress in being able to infer 3D reconstruction given a small set of views. Some of the work from our group that I cited, some other work going on and using generative models, etc. for this has let us make huge leaps in 3D reconstruction. But all of that assumes the camera poses corresponding to the input view. So I'd really argue that almost the harder task, given the current state of the field, is really how do you register these cameras? Given a small number of images, how do you estimate corresponding camera poses? Okay, so sort of formally, the task that I'm going to talk about today is, given a small number of images, we want to output sort of 60 camera poses corresponding to all those images. Okay, and when I sort of pose the problem this way, especially to this crowd, hopefully all of you just think that, by the way, we will assume that so the world orientation is aligned with the first image, just to make sort of the problem a bit well-defined. But as soon as I pose this problem that I want to go from a few images to the 60 poses, hopefully this crowd just immediately thinks of, well, Colmap sort of does that already for us, so why don't we just use that? And that's a very valid thought. And in fact, Colmap is sort of an amazingly powerful algorithm, or in general, structure from motion is an amazingly powerful class of algorithms that, given many images of a generic object, can let us understand the poses, can even give us sparse view reconstruction. But unfortunately, in sort of the setups that we are interested in, whenever we test Colmap, it's just not robust enough, because even if you have something like 10 images and we actually want to deploy these with even fewer images, there are just not enough correspondences between these views. So you might have 10 images or 4 or 5 images from sort of a 360-degree-ish field of view. And it's just, any method relying on these bottom-up correspondences is just not robust enough under these sparse views, which have a small amount of correspondences. And so, while the task that we are studying is very much related to things that structure from motion tackles, under sparse views, these bottom-up approaches really, really struggle. And so if bottom-up approaches struggle, the obvious thought one might have is, let's just have data-driven top-down prediction, and that can lead us to more robust inference. And this we've seen time and time again for other problems, segmentation detection, where we move from bottom-up methods to top-down methods and have sort of gotten robust prediction in all those scenarios. And so let's try to embrace that idea and have a learning-based approach that can presumably be more robust to sort of not having enough bottom-up matches. And we can go ahead and do that. So here is just an attempt at designing such a top-down prediction approach. So let's say we have n images. We compute some encoding of them. You can sort of use your favorite ResNet, extract some features of those images, and then feed all of them to a transformer, which can do this joint multi-view reasoning, can look at all images in context of all other images, predict some per image features or tokens. And then at the end, you can just say that, okay, give me a rotation and translation for each of these images, assuming the first image's identity, and you can sort of train this network that way. Right. So here is a very simple pose prediction approach that one might design if we wanted to have a top-down prediction architecture that sort of learns pose prediction in a data-driven way. Unfortunately, naively doing this just doesn't work. So here is just a sample result where the black cameras are the ground truth, the red cameras are the predictions, and you can see there's just a huge mismatch between the black and the red cameras. And that's because, I've chosen this object a bit carefully, it's a symmetric object. It's a ball that has a lot of repeated structures and ambiguities. But anytime you design a feed-forward prediction method, it just struggles to predict the right answer because there are sort of many possible solutions. There are symmetries in this object. You might be partially observing it. You might just not be sure that, whether a particular camera is viewing the front of the ball or the back of the ball because there are a lot of repeated structures. And if you ask any regression approach to predict a single answer under such uncertain scenarios, it's basically doomed to fail. Just as an illustration of this, and sort of maybe I'll walk through this quickly. If you have a direct prediction approach, you train it using L2 minimization error, it basically predicts the mean of distributions. So it will give good answers if the distributions are simple. It will give bad answers if the distributions are more complex. Instead, what we are advocating is to have sort of probabilistic modeling, hence the title of the talk, where instead of directly predicting a single answer, you say, okay, I'll try to model the distribution of the underlying variable and then try to infer some mode in that. And if you can do this well, then for simple distributions, of course, you'll still end up at a good answer. For more complicated distributions, again, you'll maybe end up at this mode, maybe you'll end up at the left mode, but you'll still end up at solutions that are better than just the mean-seeking direct predictions. And so this is, again, a very, very generic slide. You can ask yourself if this is valid for your problem as well, but we want to instantiate these ideas for the task of post-prediction. And to do this, we go back to this framework and have actually a very, very small change. So instead of directly regressing the rotations and translations, we say, okay, let's learn an energy-based model to capture the distribution of relative rotations. So we take the features for image I, we take the features for image J, and predict just a score that tells us if the score is high, then that means the relative rotation is likely. If the score is low, then that means the relative rotation is not as likely. So it's just unnormalized log likelihood, and we can sort of train this model using multi-view data where we know relative poses between images. And here are just some visualizations that I'll show for a couple of slides. So I'll just walk you through how to interpret these charts. So given two images, so there is one axis which corresponds to sort of changing the yaw. There is one axis in these charts that corresponds to relative rotation where we are changing the pitch. And the color of this point, which is right now blue, can change and indicates the role. So because you want to show these 3 degrees of freedom in a 2D plot, we're using the color to show you the 3rd degree of freedom. And so given these two images of a couch, our model does predict some distribution, sort of a very image under very poor lighting. So the model is still confused a bit, but it predicts these 4 modes, which are roughly corresponding to sort of 4 orientations of the couch that it can have. And the open circle tells you sort of the right mode. For this other image of a sandwich, which perhaps is a bit more texture, is taken under better lighting. The model is more sure about the right mode. But I think the example that I like the most is this one, where there is this rather symmetric object, and the model predicts basically that, okay, there can be arbitrary sort of role, and that's why you see all these colors that are centered around 0, 0. And so training it this way can allow the model to model the distribution as opposed to trying to give a single answer, which it will not do a very good job at if there is such multimodal uncertainty. And here's just a visualization. So for instance, if we focus on the bowl on the right, there are some symmetric structures. So the model is a bit uncertain about the precise relative rotation. Where it stops, it's kind of confident that it's identity, but it also thinks there may be some other modes because the object is a bit symmetric. And maybe I'll sort of skip this. But at the end of the day, once we have modeled these pairwise distributions, we can just say, okay, let's optimize for rotations that maximize the overall score. So we start with arbitrary rotations and do a coordinate ascent-based optimization to optimize R1 to Rn, such that the configuration that we get to has sort of the maximum possible pairwise score when summed across all pairs Ij. And we can just easily do this by coordinate ascent. Here, let me just visualize one iteration for you. So if we have 5 images, we have a current set of rotation hypotheses. In each iteration, we pick one rotation to update. So here we have picked sort of the red camera to update. We sample sort of hundreds of hypotheses for it, score all of them, and just update the red camera to the best scoring hypothesis. And we sort of do this a few times. In practice, about 20, 30 iterations suffice. And that basically gives us these global rotations across images. Okay. And you might notice that I've not really talked about translation estimation so far. And the reason is that we can actually get away without modeling uncertainty in translation estimation. And so the high level idea is just or high level reason why we can do this is if you dig into what translation actually means. So when we write RNT, we actually means that RNT transform world points to camera points in this way. And so if you dig down, that means that camera translation is actually the location of world origin in camera frame, and it's not sort of the location of camera in world frame. So maybe let me play this GIF again. As I'm moving the camera, the translation TI of this camera is not really changing because the world origin is at the same point in the camera frame. And so, but of course, changing the world origin does change the camera, but rotating the camera around the world origin does not. So sort of long story short, if we choose a wisely centered coordinate frame that has sort of a conveniently chosen world origin such that the ambiguities are only in rotation around it, we can get away without modeling uncertainty in translation because we've decoupled uncertainties in rotation from uncertainties in translation. And maybe I'll sort of skip a lot of details so just I can show you more results. But in our paper, we say that there is this particular look-at centered frame that we should choose. But once we do that, we can just frame translation prediction as a regression problem and not worry about modeling uncertainty, and that sort of suffices. So we can just take the features from the ith image, predict translation, and we also take the features from the first image because we just use that to determine scene scaling. So we choose a coordinate system such that the norm of translation of the first image is 1, and so we feed those features in as well. But yeah, once we do that, our system, just like Colmap, can give us 60 pose predictions given a small set of images. So here's some comparison, but actually I would argue that Colmap is a bit more precise than our system when Colmap works. The main issue with Colmap is that we had to struggle really, really hard to find these examples where Colmap does work very well. In fact, for most scenarios, if you give us a small number of images, our method can robustly infer poses that are pretty accurate, so within 5-10 degrees accuracy. But Colmap, for most of these scenarios, just does not converge or give you any meaningful results. And we also quantitatively evaluate this on this Co3D dataset, where I'll just show you some lines, but the green line corresponds to our method, and it's pretty accurate. So on categories that it has seen, it performs at about 80% accuracy, or 85. And what is more impressive for me is that even on categories that it has not seen, so completely new objects from unseen categories, it can still give you accurate poses about 75% of the time. And what that lets us do is just try our method on self-captures. So here are just some objects that have nothing to do with any of our training data sets. This is just one of our students or me capturing some images. And given these, our system can infer reasonably accurate poses. So if you look at the Gandalf statue and you look at the pink camera, we've taken it a bit from the top, and the method does understand that, and all of the relative configurations are kind of correct. And again, some more results on self-captures which have nothing to do with any of our training data. Our model can give you pretty accurate relative poses given these small set of images. As I said, we were trying to get these poses so we can use this for downstream reconstruction. Here's just a proof of concept that if you go around CMU, you can sort of find a lot of stray robots around. You can capture a few images of any of these robots, and sort of, here's an image of some images of a Baxter robot that we got cameras from, and then fed it into some reconstruction pipeline that just optimized those cameras slightly and could give us a pretty decent reconstruction of that object. So I think so far I talked about this energy-based modeling, and I'll just briefly give you sort of a couple of slides of a recent project, which will hopefully be up on archive in a couple of weeks, where instead of energy-based modeling in terms of global rotations and translations, we were looking at diffusion-based modeling in terms of equations of these rays, and it can give us slightly better results because it allows us to also use these patch-wise features unlike just global features. But yeah, just a brief advertisement. So hopefully this will be out on archive in a couple of weeks. So you feel free to look at that. And again, this works across, if you give it 5 images, it can sort of diffuse the rays corresponding to all these cameras and give pretty accurate cameras that are actually a bit better than the previous project I showed, just because it can use both bottom-up reasoning in a probabilistic inference framework. I think with that, I would like to acknowledge sort of Jason, Amy, and Deva. So all of this work was in collaboration with Deva's group, and Jason and Amy really did all the hard work. So if you have any questions, feel free to reach out to sort of Jason and Amy. The code and models for the projects that I talked about are already available. So in particular, LPOS++ is the latest and greatest model that we have, which I would really encourage you to just go and download. We also have a demo where you can just upload any images of an object around you, and sort of I'm reasonably confident that we'll do a good job at inferring relative poses for a generic object whose images you can upload. So yeah, please do try that out. Yeah, I'm happy to take maybe a question, but unfortunately I might have to run to another talk in a couple of minutes.
Okay. Thanks for the Professor Tuba. So probably we only have one question. So
yeah.
One has a question for the Professor Tuba. Okay, so probably I have one question for Professor Tuba. So basically on the real pose.
Mm-hmm.
Do you think what's your interpretation if you test the real pose for other camera models such as the visual camera or other camera model? Is it still working?
Yeah, so that's a great question. So the current model might not work as well because it's just been trained on a specific class of cameras. But I think if you could also fine tune it with a small amount of other camera data, I'm pretty sure it will work as well. So out of the box, it won't work as well. But if you fine tune it with a bit of fisheye data, there's nothing in the model that is sort of specifically assuming a camera that is, perspective. And in fact, the later work that I pointed to, which is just associating equations of rays, actually might also be a good candidate for generalizing to other cameras because it will just predict ray equations for a lot of pixels, and then later you can just recover the camera model from it.
Okay, got it. Thanks for the Professor Tuba for the great talk again. Okay, thank you. So for the next.
We appreciate the interesting and inspirational presentation from Professor Shuba. As we transition to the next topic, I'm pleased to introduce our next speaker. Let's welcome Letiza, Professor Letiza. And she will bring us the advancing the role of SLAM-based active mapping in wearable robotics.
Should I connect my computer?
Oh, yes. Do that. Okay. Okay, see you.
That's on the screen.
Yep. You need to do the sharing screen thing. Where's the yeah, here. Share and share sound. Let's go. Oh, did you need any modification?
Yes, because this one has the video. Okay. What should we do?
I think you can directly share the screen.
Yes.
It's a working one. So basically, select. Okay. And you need to unmute yourself.
Yep. Here.
Yeah.
Yeah, it's unmuted.
Unmute.
Okay. Okay, thanks.
Can you ask people online can
you hear me also online? Yes.
Okay.
Okay, so thanks for the introduction. I'm sorry for not being able to come here this morning. I was in mom's theory because my son was unwell. Fortunately, he's recovering. So today I want to talk about advancing the role of SLAM in wearable robotic systems, which is the area I work on. And more directly, I want to discuss potential applications because I just got off my lab as a neurosystem professor, so I'm really keen to hear your suggestions as well. But before I start, maybe I can give a very brief introduction about myself. My background is in bioengineering. I received a bachelor and master in biomedical engineering from the University of Naples. After using a visiting scholar, working as a visiting scholar at the New York University Environmental Center on subjects memorized FNR, and then started my PhD at Imperial College, computation estimation and understanding kinematics and kinetics for individuals with mobility impairments. I then worked as a postdoctoral fellow at Harvard University on wearable robotics and computer vision for wearable robotics. And we'll tell you more about that in a few slides. And I put my affiliation to Harvard while I'm also an assistant professor at King's College in London, where I work at the Vision and Human Robotics Lab. What we're particularly interested in the Vision in Human Robotics Lab is the intersection between human intention detection, clinical model control prediction, and clinical verification and clinical intervention in general. The ultimate goal is to have applications that can improve diagnostic, verification, and assistive devices for individuals with mobility impairments. So I can see, okay, the sound is echoing, someone is saying. Maybe there is, apologies for the interruption. Someone online says that
the sound is echoing.
The sound is echoing,
so it's still working? I mean, so system.
Maybe we should set to microphone.
I think I put this on.
Is it better? Also, the screen shows percentage of view, which is not good, but
I think we can share.
we can do that, and then we can share that, and then we can do that.
Okay.
Now, should be better in terms of the screen with respect to the audio. How does it sound now? Okay. So here are an example of studies that I have done in the past, and maybe that I can also sign up, where we monitor kinematics in a children and operate from motion capture system, and then evaluate those on individuals with motion impairments, creating modeling correlation to extract both kinematics and kinetics. But I will also extract human dynamics, as you can see on the right side, based on ultrasound, to then estimate the muscle force and use that muscle force back to the ankle exoskeleton that is this side. But why the vision is needed in wearable robotics in the first place, because even talking about SLAM, and this is pretty much like the idea of the talk today. So the state of the art in wearable robotics in general is that controls usually involves manual switch between different locomotion modes, which is really impracticable and inconvenient and cognitively extremely demanding. So we have used currently there are methods as the picture on the right hand side that are using third-phase EEG to extract the muscle information. There are a number of problems. The first problem is that the information are really limited and extremely noisy, but on top of that, you can actually send the person, for instance, if you're grasping something, only after the object is being grasped. And of course, we have vision that offers rich and immediate information about the user's surrounding, about the environment. But the problem is that most of the approaches that we have seen in wearable robotic systems have presented classifiers that support control nodes in a really limited way, or are not really giving information about the dimension, the distance of the object, and to really improve and enable an end-to-end control. So what I want to do with you today are potential like 3 experiments that I'm running in my lab, and get potential like discussion from you guys. So the first one is the idea of improving after manipulation adjustment. As you can see in this image, there is the first one where you get a wearable exoskeleton, a wearable glove, and also shoulder exoskeleton. And the idea is that by using a camera we're using different placement for cameras, we can enhance the ability to control grasping of different measures. We also want to enable more generalizable musculoskeletal modeling of ultrasound mapping, and finally enhancing locomotion in unstructured environments. So with respect to the first part, just a very brief background, the idea of if you study that propose the use of cameras for object detection and detection in general. One idea is a study that my colleague, but also a study that you're publishing in Science Robotics. And the idea is that we can use ecocentric view cameras to classify objects in the scene. But current solution primarily, as I said before, is grasping detection, but like object level perception, making them difficult for enabling intelligent wearable robots. For complex manipulations, therefore, we can say that enabling electrification and mapping of the objects in the scene can enhance current robot capabilities. We don't know that yet. These are the experiments that I'm conducting in my lab with the study that I'm about to publish. The idea is, can we have ecocentric and exocentric camera with an exoskeleton glove with an IMU, and can we use object-driven grasping to extract camera poles to build point cloud map and extract object data to their poses. And output a detailed object map with 9% freedom that uses different information together. The idea is that with a global perception of different activities, daily living and different objects in the city, particularly people with impairments and patients with mobility impairments, can we can improve their realization and effectiveness of those exercises. In a way, this is also what we are doing for clinical population for ultrasound imaging. In general, musculoskeletal model can provide insights into human biomechanics and improve clinical guidance, minimizing intervention and enhancing patient outcomes. But to obtain really accurate modeling information, we might not necessarily need MRI scans, and how can we do that? We attach on the probe of the ultrasound, the beam mode ultrasound markers of an optoelectronic motion capture system. This has been done in the past by Laura Arlo. The idea is that can we now we recently received funding to bring this idea further and to use the information from the IMU with the information from the mode ultrasound to create a mapping and localization of the ultrasound of a generalizable model of the art. And kind of like the last potential components that we are also investigating in my lab, that we've been investigating in the past months and a half, since I set up really my lab, is the ability to use mapping for wearable robotic system. In the past, I used ultrasound and the force extracted from ultrasound to improve in real time the navigation infrastructure of the environment, and studies that presented also that locomotion mode patterns to control wearable robotics across different levels of terrain, level ground, incline, decline. So individual components were in the past evaluated individually, but not really support how users would navigate infrastructure environments. So the idea here is that using Intel real-sense cameras, which have embedded IMU and embedded processors that run the embedded SLAM algorithm, we suggested that while the user was walking into different environments, we could set the different locomotion modes based on the different walking that you are outputting to really tailor the assistance according to different terrains. So just to recap what I said, the overall idea is we could potentially use localization mapping to improve accurately manipulation grasping capabilities through exploration strategies that tackle the potential to actually improve tailored assistance strategies. We can fuse IMUs and BIMO to create more detailed master-data models and move outside laboratory settings. If we think about an electronic motion capture system, it is extremely accurate in the field of biomechanics really used, but is not really available in clinical settings. So this would be an approach that we use in clinical settings. And the final thing is applying algorithms to localization algorithms to improve the identification of user work with different terrains, and based on the information that we gathered in the lab, then changing the locomotion mode accordingly. So overall, bridging the gap between navigation, exploration, and human biological signals, which are taken into account either with surface EMG or with ultrasound, is an environment that is particularly in my lab at a very early stage, but presents new opportunities. And I'm very thankful to my team, and I'm happy to take questions. Oh. Hello. Yes. Okay. Well, actually,
Hi, Professor. Are you here?
Yes.
It's online.
Yeah. Yes.
Okay. Let me stop sharing.
Okay. Let me know when I can share my screen.
Sure. Yeah, you can share your screen now.
Okay.
It works.
Do you see the the full screen, or do you see the presentation mode?
Oh, it's not a full screen.
It's not full screen, but we can see you.
What about now?
Yeah, it works.
It's working now.
Okay. Yep. Great.
Hi, Professor. I think you can start your presentation.
Oh, okay. So I thought that I should start on time, but I can start earlier.
Yeah, I think we can start. Yeah. No.
Okay.
Okay.
Okay. Then I'll start my talk. Thank you very much for inviting me here, and actually great pleasure for me to present this work to you. I wish I could be there at ICCV, but I'm in Detroit, as many others. Today, I want to talk about the SLAM, of course, but I want to introduce some of our work that we try to integrate the learning with the SLAM. So in the title, I said high-level scene understanding and the non-conventional sensors, and you will see what do I mean by that. So our group, the SLAM, and in doing so, we incorporate many different sensors, LiDAR and camera, but not only that, like for example, the thermal camera or sonar for underwater, radar for a very turbid environment or very foggy and hazardous environment, and even camera. So our group is reaching towards some non-conventional sensors beyond the visible spectrum too. But why we are doing so is to overcome many challenges, not only the visual appearance changes, but also the structural changes too. And today, the three topics that I prepared is about how to overcome those challenges. The first one is I want to introduce how we can use live, little higher level information in the place recognition. More specifically, what we want to talk about is how to handle lines, how can we handle lines better, and how to represent them and match them. And the paper title for this work is A Line as a Visual Sentence. And the second topic is might be weird to see some manipulation thing in the SLAM workshop, but this is about the pose estimation for a target object. In the manipulation, you need to know the pose of the object to reach out and grasp and do manipulating. And then to do so, we need 6 of pose estimation for the target object. But what we realize is we can change the problem and treat it as an object SLAM, and treating each object as a landmark, and we can solve this one within a SLAM framework. And in doing so, what we try to do is actually we can combine the kinematics with the visual information. So the kinematics can be thought of as odometry, and the visual information, making like visual look closures or in a SLAM. To combine those, what we need is we need covariance or uncertainty associated to each measurement, because the deep learning will give you the predicted mean, but also it'll be nice if it gives you the uncertainty associated with it, so that we can combine that with other factors like, for example, the kinematics or other sensors, right? So that's the second topic that I want to talk about, how to estimate the uncertainty from the deep learning. And the final topic is about the non-conventional sensors that I was mentioning. So our group is heavily investigating using thermal infrared cameras, and we wanted to use the many deep learning for the thermal images for the, like for example, the optical flow estimation or object detection. But the problem that we are encountering is the lack of data. And the question we had is how to secure the enough training data for the thermal infrared images. So the third topic is about how to secure the data set. And also, if it is not sufficient, how can we leverage already existing labels from the RGB image and kind of extracting that from the RGB image by using the image-to-image translation. So those are kind of a review of today's topic, and I want to go one by one. The first topic is about the line as a visual sentence. And I want to make a note that all of the the thing that I'm mentioning, we released code and a data set with it. So please visit us, our website, and you can actually see the code and data set. So for this using a line for the visual place recognition, there have been a lot of conventional approach. They try to use a feature point. How do we do that in the computer vision community? Is considering a word or a feature point extracted from an image as a visual word. And you look at the statistics distribution of the visual word to see if the scene has been seen before. Have I been here before? But what we think is, if a point is a word, a line in an image would be a sentence, and the line-to-line matching would be a sentence-to-sentence matching. And what we want to tackle this problem is, okay, let's apply there's many sentence-to-sentence matching in a language model, and we can just adapt that and apply this to the computer vision and see if we can make the line matching working nicely. So this is captured from our final work, and as you see, the lines are pretty well matched across the images. And as I said, we are treating a line as a set of words. It's a sentence consists of many words, right? This line, the visual line, consists of many visual words, and you see, if you look at the attention, you see very high importance is occurring at the corner point. That's actually obvious. And why we choose this line as a sentence matching, another key important aspect for that is when we try to match lines, there could be cases when the sentences are truncated, like line could be occluded when we are moving and when we are changing the viewpoint. So this is really nicely handled by the sentence-to-sentence matching. The previous work, they tried to cross the pixel distribution over this band over detected line, but our method incorporate the transformer to have this line descriptor. Here we have more simpler example. So for example, if this is a sentence with the 4 words in it, we have each one of the visual words, we actually use a super point for this visual word, and we make this line consist of 4 different visual words and have the position encoding and use the transformer to encode this for us. So you might notice that this line descriptor is already very descriptive, and it can maybe directly used for the line matching, but we actually have another module right after that. We don't directly use this line descriptor directly, but we looking at this one in using a GNN. We try to look at the geometrical correlation among the line distribution, because what we try to do at the end of the day is the place recognition. So this is kind of really helped in doing so. So this is our final line descriptor after the GNN, after the line signature network, and this is what we use. For the line detection, we use the line segment detector, LSD, for the detection. And for the words, visual words inside the line, we use the super point. So the next to ask is how to train. So we apply this one both in a self-supervised and supervised manner. For the self-supervised manner, this is widely known technique. Using the homography adaptation is known homography, you know where the points will be in the other image. So you can use this one for the self-supervised manner. You can train our network in a self-supervised manner. And also, we use the ScanNet that has nice ground truth. So we also train the network in a supervised manner too. So in total, we secured pretty much abundant data set for the training and also for the test data. And this is our qualitative result, and it's working fairly nicely compared to other existing methods at the time. But one thing that I want to make note is that this last column here, the outdoor visual localization. This is from the Oxford data set, because why this is important for us is because this one is showing us the generalization capability. because this is on-scene data set. And if you look at this one, if we consider the correct answer within 1 meter bound and 10-degree bound, then our approach could almost achieve 90%, which is very impressive, even in the on-scene data. So here's a live demo that I want to show you. So we freeze the first frame and I'm kind of moving into the scene, and you see the lines are matched across the scene. There's a huge perspective changes, and this is quite cluttered environment within our student office, and you see the lines are matching, and this was quite working well. But I'm not saying we should use only lines, but what I want to say more is the line and points are really complementary, and if we combine, we use them both really, then that really helps, because many cases in certain portion of the image has point feature, abundant point feature, in certain portion of the image has more abundant line features. So if we use both, we can have well-distributed features, and that really helps in both audiometry, place recognition, and line matching. All right, so with that, I want to move on to the second topic, how we want to combine the deep learning into the graph SLAM toward the robot manipulation. Basically, this is an object SLAM. The object pose estimation problem is to to estimate the relative transformation fixed off between the camera and a target object. And as you see, this bounding box is visualized over using the predicted mean that we got from the deep network. And this is very important. We want to reach out an object to grasp and manipulate, and we want to know how the object is at with respect to the camera. And some typical assumption that we have for this is we want if the object is asymmetrical or symmetrical in advance before actually reaching out, so that we can get the proper CAD model. But what we want to say is sometimes the asymmetric object may become symmetric depending on the viewpoint. For example, of this mustard bottle, this looks very asymmetrical, but if we change the viewpoint, then this becomes suddenly very symmetrical object. And what we want to do is we want to know when this kind of degenerate case happens by looking at this certain measure. So in this work, what we try to do is we try to estimate the uncertainty or confidence associated to each one of the axes, object axis. How we do that more specifically is we have this model, and they're associated primitive image that actually the three different axes, X and Y and Z, RGB. Each axis is color coded by RGB, and whenever we reconstruct this target object, we also reconstruct this primitive image. This primitive image will directly give you the orientation information about the object. So we are enhancing the orientation estimation perspective. But we are not only doing that, we can also look at the quality of the reconstructed primitive image to measure the uncertainty associated with each direction. So each one of these axes will give you we are kind of predicting the uncertainty associated with each direction. And at the end, what we can do is we can incorporate that as a covariance in our post-graph SLAM framework. So here I'm showing you the video again, but this time please look at this right-hand side. Here, how the primitive axes are reconstructed. They are well reconstructed when things are okay, but when the scene is becoming degenerate case, you see this quality of the reconstructed primitive axis is getting worse, and you see this kind of measure of the uncertainty kicks up the threshold, and this is indicating that we cannot really believe in terms of the X and Y axis. Only the Z axis is something that we can believe. So we can incorporate this information into the as a factor in a Postgres SLAM. And if we solve it, because this is an object SLAM, what we can see is a SLAM. So you see the landmark or object appears and it moves a little bit, but as we make more measurement or look closer, then it stays there. For example, here on this small screen, it's being refined. You see things are moving a little bit, but as we make more measurements, it's kind of stabilized and refined. So this is something that we have done before, and now we are reaching out to more challenging objects like transparent objects. There are many transparent objects in our daily lives in a lab environment and recycling center, right? And the problem of the transparent object is really hard to detect those. So this group, the previous work was done by Dr. Jun, and together with Jung-Yun Kim, and they are working toward this transparent object manipulation and detection and object estimation. And actually, we have recently released our transparent object data set, and they are actually probably in that room. So if you want to ask more about this manipulation object SLAM or transparent object data set, please reach out to them. They should be able to answer better than me in person. All right. So the last topic that I want to talk about is the thermal infrared images. So our group has been working on this thermal camera SLAM for a couple of years now. This is a result from when we run the direct SLAM for the thermal images, from the thermal images. Thermal image has been known as all-day vision. So you see the map is reconstructed nicely. We can estimate our trajectory regardless of the illumination condition, day, night, and you see from this little thumbnail, the RGB image is very dark and it's really hard to see. You can probably apply the deep learning to enhance that, but thermal camera by naturally, it just gives you the nice infrared information, the temperature information, which we can use directly for the direct SLAM. It's just changing from the photometric error in the RGB to the temperature residual. So basically, things are very similar, and you can apply this one for the thermal camera. So we were working on that part, and we realized there are not enough data set for the thermal images. So last year we published a data set, stereo thermal camera data set. This has stereo rig of RGB and stereo rig of thermal camera together with a LiDAR. LiDAR can be used as maybe sensor fusion and for the ground truth provide. So this data set has been captured changing the time of the day from the dawn to afternoon to the evening. So you see the temperature histogram is changing a little bit. So that we have a variety of the temperature distribution within our data set. We try to secure more and more real world thermal data set, but that was not enough. What we felt, we want to do more, like many deep learning and many more with the thermal images, but we realized the data is still not enough compared to the RGB. So what we think is maybe we can use the well-labeled data from the RGB by distillation of the labels from the RGB images into the thermal images using the image-to-image translation. So there are, for example, if we want to train our thermal image for the optical flow, labeling optical flow is very tricky and difficult. But if there is well-labeled optical flow from the RGB images, what we can use is just change the RGB image to the thermal image through the image translation and just use the labels from the RGB. So that is the idea of doing this. Something that we wanted to make a note is we tried to use a multi-domain, not the bi-domain, because you can think of the thermal image. This is thermal to RGB, so this might be a bi-domain, but it's not, because thermal has many different distribution, like the one that you saw before, like day, night, evening. So many different styles can exist, and this multi-domain style selection really helped us to make a more realistic thermal images from the RGB. And here is a quick video, short video that we tried to compare to the bi-domain translation. This multi-domain really helped. We translated from the simulation images, but also from the real images that we have, and many other real images that exist in the community. You can use this one. And what we did from it is in the result, we try to see if this one is working for the optical flow or object detection. And we are actually stemming from that toward the more various tasks in the thermal image. All right, so here's the conclusion. So we want to tackle the long-term deployment, and we wanted to secure more robustness, and we're doing that in many different ways. If we can, as long as we can apply the SLAM framework, even including the manipulation task, we want to see high-level features like lines, or we want to see if we can combine certain uncertainty aspects into the postgrad SLAM, or can we change the sensor modality totally to the new hardware to see if we can overcome many challenges. So those are something that I wanted to highlight from our work, and this work has been supported by many sponsors. And for the manipulation, we have been working with Professor Jiwan Liu from KAIST, and for the translation, image-to-image translation, we have been working with Professor Youngmin Jo from Ina University. Yep, with that, I want to conclude my talk, and thank you very much.
Actually, Professor, I have a question.
Yes, yes.
Have you considered applying your method to some challenging conditions, for example, the snowy day or smoking conditions? Since
that's a very good question. I didn't put it in my slide, but the motivation, why I started working on thermal and radar is we had a project to put a robot into the disaster environment with full of smoke and fire. So in that kind of situation, thermal camera can see better than the RGB, but still has some limitations. So we actually reach out further to the radars for that kind of case. So yeah, unfortunately, due to the time limit, I couldn't really talk about that a lot, but thermal camera has advantage in the more disastrous environment when the visibility is degraded severely. Yes.
Oh, I see. Thanks. So.
Okay, thanks, Professor. And I think we can move to our next speaker.
Okay, thank you.
Okay, thank you. Okay.
Hi, I can share the screen if that works from your side.
Okay, so let's have our, okay. Share my screen right now. Wait a second. Okay, so hello everyone. So let's have a quick introduction for the Professor Michael Case. So Professor Michael Case research focused on the efficient inference at the connection of linear algebra and the probabilistic graphics model for 3D mapping and localization. He has previously been the research scientist and a postdoc associate at the MIT with the Professor John Lerner's Mind Robotics Lab. In 2008, he has received his PhD in computer science in the Georgia advanced by Frank Dallett. So welcome to the Professor Michael Case, and he will introduce topics on the learning for sonar and radar SLAM. Okay, so let's.
All right, thank you for the introduction.
Wait a second, and let's see you to share my screen. Stop share. Okay, Professor Michael Kiss, I think you can share your screen now.
Okay, sounds good. All right, thank you very much for the introduction. Yeah, today, similar to Ayang, my group is working on some non-conventional sensors such as sonar and radar. And so today I want to talk about these two specifically. So sonar, why do we want to use sonar in the first place? So if you have worked with any underwater robots, and unless you went to coral reefs maybe, you probably ran into issues where you couldn't see much. Visibility is pretty low using cameras. In some of the environments that are really relevant for robots, near shore and harbor environments, you essentially have to almost run into an object before you can see it. So maybe at a very short range, if you get close, you can use cameras, but for anything else, this does not work. So this means we have to revert to acoustics. That's basically the only thing that works underwater. And there's some pretty good sensors around nowadays, multi-beam sonars that also work with high frequencies, so they can work in short range and give you pretty high resolution, so tens of meters. But you can also look far out if you want with lower frequencies, and you can look out for kilometers with that. So sonar is really the mode of choice underwater. Nothing else really works. And radio also doesn't propagate, so we have no GPS. So we really have to use that to also do localization. Okay, what are the challenges with using sonar? The first problem is there are no good features or descriptors. So if you try to do SLAM, the community is relatively small for sonar, working on sonar. And if you compare this to the vision community, it took decades to develop good feature detectors and feature descriptors. So the question then is, how can we do this? Of course, in the vision community, recent learning methods at least get to the same level or outperform traditional classical methods. So it doesn't make much sense for sonar to go through this process, which is do learning right away. But that gets us to the second challenge. There are no large data sets available. Right? In computer vision, huge amounts of data, learning is relatively easy. Here, we have to develop specific methods that can work with the little data that is available. Maybe use post-supervision, so similar ideas than have been used on the computer vision side. The next challenge is sonar geometry is different. So we have to account for that. It's still a projection model, same as with a camera, but instead of losing the range information, you're losing the elevation information, basically the Y coordinate in the image. So an image does contain range. So each cell here corresponds to a certain range and to a certain bearing angle, but the elevation angle is unknown. So any object along an arc within the aperture of the sonar will project to the same pixel. And even worse, if there are multiple objects along this arc, the intensities will add up. So this is very different from the computer vision case where we work with rays. And we can adapt computer vision methods, basically similar ideas to structure for motion. This is now pretty old work that we did a number of years ago, where we extract features, correspond them, and then set up an optimization problem that instead of doing bundle adjustment, it basically adjusts bundles of arcs to get the geometry. There are degeneracies in this that have to be taken into account. So this was one of the main challenges, but this can be formulated in the right way in the optimization so that we don't actually recover necessarily the full 3D position of landmarks, but we still get the full benefit of their measurement in terms of localization. So these methods work quite well, but they have a limitation. You need to detect features. And how do you do that? So the community went through basically all of the computer vision features, and there's really only one that works, that makes sense in this case with these very noisy sonar images, and that's ICCV. And it works decently well, but it's kind of challenging. So you can see here correspondences before filtering from ICCV. We also used Superpoint and LightQ, some learning-based methods, and that also doesn't perform very well. And so our method here that's specifically trained for the sonar geometry and takes into account that the viewpoints change. As the viewpoint changes, the geometry, the image changes in different ways than for cameras. Excuse me, I'm getting some echo here when I'm talking. Maybe if someone can mute, that would help. Okay, so, all right. So basically computer vision approaches don't directly translate, but we can do similar learning methods than have been used in computer vision. So taking into account that we don't have a lot of training data, we use a method that uses camera pose supervision. So if we can get ground truth for the robot pose, then we can use that to supervise the responses. And so in the computer vision side, this was done by exploiting epipolar geometry. And there's something equivalent for sonar images. In the community, it's known as epipolar contours. It's a bit different from epipolar geometry that you'll know. That's basically projections of arcs into another sonar image. And what you end up with is a small curve along which a corresponding feature has to lie if you know the relative pose between the two sonar images. And so with this, we can define losses, cyclic and epipolar loss, and we can do training. And so the resulting method performs quite well. Here's a simulation environment. This is using HoloOcean underwater simulator with a somewhat strange environment and above water environment that's been kind of flooded for this, or we simulate sonar in there. And on top, you can see ICCV features, again, before any filtering. So the responses are not so great. This is what we've been relying on so far to make it work. But you can also see there are not many features in the first place. So that makes this really challenging to get good results. And so with ours, we can get some pretty good correspondences. There's still some wrong ones in there, but again, this is without any filtering. And this is, of course, with simulation. So we also had to do this in real setting. This is in our test tank. We have a couple of objects on the ground to get some interesting features. And on the right, you can see from different viewpoints the sonar correspondences compared to a first image here. Now, this image actually does include rotation. So there are, the vehicle rotates, even though this is not obvious. It's not obvious because this structure up here looks always the same, but this is actually an artifact from sonar imaging in the tank. That's basically from echoes inside the tank. So the rotation of the sonar is also changing. And you can see this in the correspondences that they kind of shift across. So this performs quite well. This is kind of the first time we really have decent features and correspondences to work with, which makes localization much easier. So here we're comparing numerically our approach, Sonic, to the ICCV and LightQ alternatives, and simulation and on real data. On the left side, you can see inlier ratio, so significantly better here. On the right side, you can see a relative pose error, and this is based on using these correspondences for doing acoustic bundle adjustment. So there's basically the acoustic structure for motion, the optimization back end of that, using these features. And again, this significantly outperforms what we could previously do. So this provides localization for the robot. Now the question is, the sparse features are not useful for navigation, so can we do dense mapping of the environment from this? And so dense mapping with imaging sonar is a quite challenging topic that we've been working on for a couple of years. And we finally, using learning approach, got some quite good results here. So here's a test structure that we used in the tank. We're not looking at simple geometries here, but more stuff that you would find in infrastructure So there's more complex topology. And so what we did is basically a north-based method, but adapted to the acoustic geometry. And so what we do is we represent 3D surfaces as neural implicit functions, zero-level set. Then we define a differential renderer. This is really the key, modeling the acoustic spherical wavefronts. So you can think of acoustics as wavefronts emanating from a certain point, but you can also in the propagation at any given point do the same thing again, and from there it's again a spherical propagation of the wavefront. And so with this model, it's possible to define this volumetric differential renderer. And then finally, we need some regularization to get good surfaces as usual with NURF models. And so the image formation model differs a bit from the vision case. The first thing is we have to integrate over the elevation arc. So it's not just along the ray. Then we have to account for spherical spreading. So that's different, not array again. And then the transmittance is a bit different, but that is a well-known quantity. And so one of the things that changes in NURF, you would sample along a ray, but in this case, it's really a slice through space that we need to sample from. We basically don't know where along the slice the feature lies, and therefore we have to sample from that and then sample along a ray. So this complicates things a bit. But if we combine this then with the regularization, both an iconal loss and another regularization loss, we get quite good results in the reconstruction. So here's a simulated sonar. There are ground truth objects on top. We have belief propagation and ADMM. These are the previous state-of-the-art methods. ADMM is something we developed in-house. And our method can be shown at the bottom. So if you haven't worked with sonar before, these are really awesome results, right? You can actually see what the object is in this, and you actually have quite some details available. So this was quite surprising. But again, this is simulated data. So we had to do this in real experiments. Here's again the water tank with different test objects, including this structure was used. We got a ground truth mesh from that object using laser. And then the results can be seen here. The difference to before is that the columns here show different kind of sonar. So one is using 1 degree opening. So this is basically a bit more like a laser range file as a profiling sonar. That's relatively easy. And previously we could solve that. We got the right topology. But with a more common imaging sonars with larger aperture, previously the topology could not be resolved. And so our reconstruction here in all cases gives us the full topology of the object. So this is quite some progress here. And yeah, so with this, I want to switch to a different sensing modality, which is radar. So this seems very different, right? We're going from water to air, and from acoustics to radio waves. Seems like this is completely unrelated sensor. It's actually not. So millimeter wave radar is very similar to imaging sonar. It's a phased array. So this means you have an array of transducers, or in this case, an array of antennas. And with that, you're determining the direction from which energy gets reflected back from the environment. And so this allows to get the bearing angle. For this specific radar, TI radar, cascaded millimeter wave radar, which uses 4 chips that are typically individually used for cars, for example, for collision avoidance. With 4 of these, you get more antennas and therefore better spatial resolution. And so they distributed them so that you get most of your resolution in bearing, but you also get some resolution, some resolve in elevation. So it's really a 3D radar. So there are no moving parts, completely solid state. works with or without light, in bright sunlight or with no light. And it also works through smoke, as Yang mentioned previously. So that's a very interesting sensor. Theoretically, could be very cheap in the future. I mean, they are commercially being used as individual chips for cars. One thing that is different to sonar is it does provide Doppler velocity. So you actually get velocity measurements at the same time. Theoretically doable with sonar, but the sonar sensors that are commercially available do not include that, and the resolution will probably be fairly low. So here, because of the really high frequency compared to sonar, you can get much more information, but it's still very noisy. There are artifacts because of the phased array. So it took us a while, and it turned out my original idea of using the sonar-based methods on radar did not work out very well. So we went back more to classical approaches, and we came up with a way to do radar inertial odometry. And that means you combine an inertial sensor with a radar. And with this, we can walk through a building and get a pretty good trajectory, as you can see from the features, the radar features that are being mapped here. So you can actually see basically the shape of the building also. This is only doing odometry, no loop closure. You can see some duplication of walls here. We've also done loop closure in between, but this here shows you that the drift is actually quite low in this. So it's a quite competitive sensor compared to laser or vision, not completely as accurate. And of course, the mapping is not as good because it sees different features. In fact, it sees the structures inside walls, and it also sees through walls. So you get some structure behind, but you also get artifacts from reflections. So there's definitely work to be done on the mapping side. Now, this works very well here, but there is drift in Z direction in the height. And if you try to do this in a staircase, it actually fails. You have very quick drift. So we determined that this is because the low resolution and elevation. And so our workaround here is to use two different radars, 190 degrees off. And in the future, I think there will be radar systems around with antennas equally spread in both directions. That would solve this. But the current workaround is to simply use two of these and have them operate at different frequencies, right? So we actually have to reprogram them. They are typically for outdoor environments, long range, and not very good resolution and velocity, but you can reprogram them for shorter range and get good velocity resolution, Doppler velocity. And then also use two different frequency ranges for the two radars. And so with this, we can here go, including stairs, go through an environment back and forth, and we have almost no drift over that course. Another couple of sequences, different environments, including even a spiraling trajectory here, stairs, and just normal hallways in between. And so all of this works quite well. We can evaluate this against ground truth, or actually visual inertial or LiDAR inertial odometry, in this case visual. And here you can see if we just use the horizontal in green, we get significant drift in elevation, tens of meters. If we rotate the radar, so vertical orientation, we can get rid of that drift, but now we have drift in X and Y. And so with the dual configuration, we're basically getting close to the visual inertial solution, and we get pretty good trajectories out. We can also do mapping with this. So we can extract features from the radar. Again, we did a learning-based approach initially that didn't work so well. I'm not completely sure yet if that was us not doing the right thing. But so we went back to classical methods. So we are using C4 here, which is a typical radar feature extractor, radar target extractor. And with this, we can map stable features in the environment. Now, of course, these are not dense surfaces, right? So this is one thing that's missing. And there's a question, is there enough information in the radar data? My feeling is there may be, right? Not everything reflects as well, right? So surfaces are a bit less clear. But I think there's a lot of data in the radar that we have not exploited yet. And this is clearly a place where learning will have to come in. It's completely not clear to me how classical methods could deal with this. So in summary, I talked about SONO, learning correspondences, neural dense mapping, both learning approaches. The neural dense mapping I really like because there isn't a generalization issue here, right? You're not pre-training anything. You're just throwing the data at it, the images, and you get a 3D model out. So it's basically an optimization method using a compressed representation of the geometry. That's one way that I'm thinking about this. For radar, at the moment, mostly classical methods. I think this has to evolve a bit, especially dense mapping really has to use learning. And in case you're wondering that I didn't talk about backends at all, I will. I have another 1 or 2 slides. I think I still have a minute left. That's mostly classical methods. So what we've used here are all classical backends across for sonar and radar. And there are further developments in that direction. So recently we published a robust backend that you may want to take a look at. This is based on graduated non-convexity from MIT, which is a batch method. And so we incrementalized this. We basically combined this with ISIM. So now you can have a robust solver in ISIM that is beating all the other robust solvers for incremental approaches, which are different from the batch case where you have all the measurements ahead of time. And a few other recent developments that are not published yet but will appear soon. One is on distributed smoothing and mapping. So asynchronous, so especially if you're underwater, very unreliable acoustic communication, low bandwidth, targeted to that. And we can exchange as little information as possible and get, and also no information if there's no connection. And we get basically the best solution we could under these conditions. And one place where learning does come in again, but more traditional in terms of optimization, we can actually tune sensor models automatically. So learning covariances in a way that is safe so that you don't get covariance matrices that are rank deficient, for example. Okay, so with this, I'd like to end the talk and I'm happy to answer any questions that you might have.
Hi, Professor. I have a question.
Yes.
Yeah. Since the traditional radar sensor cannot capture accurate Z-direction information, and I think your proposed, which is a dual radar, this approach are pretty interesting. I'm wondering, have you tried or considering utilize the 4D radar sensor, since it can relatively capture some accurate vertical informations?
Which sensor specifically?
4D radar sensor.
Yeah. Oh, yeah. So it's typically currently a compromise between, right? So for the TI radar, they decided to put most of the antennas in the bearing direction to get as high resolution as possible. So it's equally possible to distribute these antennas equally. So you're basically losing some spatial resolution in bearing, but you gain the resolution in elevation. And so, yeah, with that sensor, you could, they are not completely there yet, I think, in terms of resolution, but I think that will soon be the case. And with that, you would only need a single radar. So you could do this right now. If the antennas are equally distributed, you're just losing accuracy because you don't have the angular resolution that the TI sensor has in bearing right now.
Oh, I see. Thanks for answering.
And so these,
Thanks for sharing such interesting contents. And I think that's all for this workshop. I want to say thanks to all of the speakers to sharing cutting edge, and also inspirational contents and works. I also want to say thanks to all the audience, no matter virtually or in person. Thanks for participation. Thank you. Hope you have a nice day.
Or is it the Zoom time?
Oh yeah, sure. Let me check. Michael, you mean Professor Mike?
Yes, still here.
Yeah.
Okay. Hi, Professor. I just have one question.
Sure.
With this latest paper, you're doing the learning covariances for estimation. Because I'm working on bi-level learning. I saw your paper on arXiv. I just wanted to know if you're planning to release a source code for this one soon.
That's still in the works. I'm actually not sure what Mohammed's plan is on releasing. So oh yeah, since you saw the paper on arXiv, maybe best to shoot an email to Mohammed.
Okay, I'll just ask him. Yes, because I am looking into this, and this one covariances for state estimation, which can be used for uncertainty too. I'm very interested, so I'll just shoot the email. Thank you.
Hey, Michael.
Okay,
it's
sounds
me,
good.
Daniel. I don't know. Where's the camera?
Can you use the camera here?
I don't know. Michael Case, it's me, Daniel. I'm here at ICCV.
Oh, hey, how are you?
Good, like your talk. I didn't even know there was going to be an air lab workshop. So I was like just walking by and I was like, oh. Well, that's it. I don't have anything to say, but I hope things are good. Are you at a are you at
So I'm at IROS actually right now. I'm at IROS in Detroit right now.
Yeah, right. Yeah, I think that's where everybody is. Yeah, IROS. Yes. Well, Detroit is fine. But yeah, well, that's it. Okay. That's all I have to say. But yeah, thanks. So I don't know. Should we shut it down?
Okay, thanks for inviting me. See you.
See you.